Hi, in this video we are going to introduce a string. A string is a sequence of characters. Now many of you must be wondering, we already have arrays. We have integer array, character array, array of objects, array of strings. Why do we need a separate data type or data structure string? Why can't it be just a character array? The reason that makes a string special is a small set of elements or small set of characters. In strings, you typically see very small set of characters. Like if you talk about English sentences or English strings, and if these are lowercase English character strings, then you will have only 26 possible characters. And if you allow uppercase, dot, comma and other things, then also it's very small set. There are 128 standard ASCII values that cover most of the characters that you generally see, and also have some extra control characters. The first 32 characters in ASCII are control characters, and then you have English lowercase, alphabets, uppercase, and some special characters like smaller, greater, hash, dollar, comma. All these characters are covered in these standard 128 characters. So this limited set of characters make strings special, and that's what makes many standard algorithms and many tricky questions on string data structure. Now talking about these English characters and their codes, in English we have A to Z 26 characters and lowercase, and then you have uppercase A to Z 26 characters. And multiple languages encode these characters or encode the character data type in different ways. For example, C and C++ char data type uses ASCII and stores characters using 8 bits. In Java, character data type or char data type is UTF-16 and stored using 16 bits. Now what is ASCII and what is UTF-16? ASCII is one of the oldest formats to store the characters. Here you have 128 standard ASCII values, and then since you have character as 8-bit, most of the platforms, most of these languages, they use extended ASCII format where they add 128 additional characters to extend the ASCII and to use this 128 character. Why did we have only 128 characters? The reason is historically we used to have a parity bit, which was no longer needed. So people came up with the idea of extended ASCII form and started storing 256 different characters in the ASCII. But 128 characters are always same as standard ASCII. First 128 characters are same as standard ASCII characters. So this is about ASCII. Now talking about UTF-16, UTF-16 is a Unicode standard format. What was the need of Unicode? In ASCII, we only have English characters. There was need for larger character set to store characters of other languages. And that is why Unicode was created. UTF-16 is a version of Unicode implementation where we store 16 bits to store characters. And the great thing about UTF-16 is the first 128 characters and their encodings are same as ASCII. So if you are programming in Java and if you take a character and if you assign it to an integer, you will get its ASCII value even if it is storing UTF character store. For example, small a has ASCII value 97 and small b has 98, and all these are contiguous values. C has 99, then D has 100. Capital A has value 65, and these are also contiguous. Capital B has 66, then capital C has 67, capital D has 68, and so on. And these contiguous values also make these English alphabets or the questions on these English alphabets really, really interesting. I'll talk about an example in this video only. So UTF-16 is for larger character set, and Java adopted this Unicode format and has this format of 16-bit characters, which allows a larger character set. Java also has a data type byte if you want to store smaller values. Similarly, C++ also has a data type wchar_t for storing the wide characters, which are Unicode characters. But by default, char is 8 bits in C++ and C and char is 16-bit in Java. And this is how their classes are also. The string class in C++ uses normal 8-bit chars. The string class in Java, it stores Unicode characters, 16-bit chars. But the algorithms that we are going to discuss, the implementations, the tricky questions that we are going to discuss, there we can notice that both C++ and Java are going to have similar implementations. We can convert characters to integers and we will get the same values because UTF-16 has same first 128 codings as ASCII. And they're contiguous in both. So since they are copied to UTF-16, so they have to be contiguous in UTF-16. And these characters have contiguous values like 97 for A, 98 for B, 99 for C, and so on. Before I discuss an example problem on string, let me clarify what I just said. In C++, if I assign a character to a variable and then if I print its integer value, I'll get the ASCII value of that character. The output of this program is going to be 97. And if I replace this A with B, I'll get 98. And if I replace this A with C, I'll get 99. Right? If I write this snippet in C++ and run it, I'll get 97 here in this code. Similarly, in Java, even if there are Unicode characters, UTF-16 is used. If I assign A to a character variable X and if I print its integer value, I'll get 97. And if I replace this A with B, I'll get 98. And if I replace A with C, I'll get 99. So this is the idea of internal storage of the characters in a string. So now we get an idea that characters are English characters from small a to small z and capital A to capital Z are stored at contiguous locations. And in fact, most of the generally used characters are those standard 128 characters that we typically use. Let us now see an example problem to get tricks of a string data structure. Let us say that we have a string like GeeksforGeeks and this string contains only lowercase characters. Our task is to print every character and its frequency. And we need to print these characters in sorted order. The smallest character should come first, then the next character, then the next character. So if you see this string, the smallest character is E. So we need to print the output as E and its frequency 4. E appears 4 times, 1, 2, 3, 4. Then the next character is F and its frequency is 1. Then the next character is G and its frequency is 2. So we need to print this output for every character. We need to print it and its frequency. Now imagine a situation when these characters were not limited, right? This was an integer array and you wanted to print every integer and its frequency. What you could do with this integer array? You could use a hash table, and if you use a hash table and put all the integers in the hash and then traverse the hash, you won't get the output in sorted order. So you will have to do something else. Other solution could be you could first get the hash entries in an array and then sort it. Or you could use a cell balancing binary search tree and store items and their frequencies. But all these options lead to the time complexity n log n for an array of integers of size n. When we talk about a small size alphabet, strings, we can solve such problems much more efficiently. For example, here is an implementation that is big O of n time. Since the alphabet size is only lowercase, and these characters have contiguous ASCII values. When we use these characters as an integer, we get contiguous values like small a for 97 for small a, 98 for small b, and so on. So what we do is we create a count array of size 26 and we initialize this array as 0. This is how we initialize and create an array in C++ and this is how we create in Java. And these are the contents of this array. Initially it's all 0. Index 0 corresponds to A, index 1 corresponds to B, and index 25 corresponds to Z. Now what we do is we traverse through the given string, we use individual characters as indexes. That's the trick that you see in many string questions. When we traverse this string from G, the index of G in this count array is 6, right? G comes at 7th position in the English characters and index would be 6. How do we reach the index 6? We know that all these characters are contiguous ASCII values. So if I use this G and I subtract the ASCII value of A, I'll get the index of G, right? I'll get the ASCII value of G would be 97 plus 6. So I'll take that ASCII value, subtract A's ASCII value, I'll get the index 6. So I go to that index and increment the G's frequency by 1. Earlier it was 0, now it becomes 1. Now I come to E and increment its frequency by 1. When I process all the characters, I'll have frequency of every character in the string. So these are the indexes 0, 1, 2, 3, 4. So this is index 4, right? This is index 5, this is index 6 corresponding to G. And you can guess the remaining indexes. So at every index, I have the frequency of the corresponding character. Now I want to print these characters in sorted order and their frequencies. So what I do is, I again do one more loop, and this time I traverse through the count array, not through the original string. I traverse through this count array and I'll get the indexes 0, 1, 2, 3, 4, 5, 6. I want to get the corresponding characters. So what I'll do is, I'll add the ASCII value to every index. So if it is A, I'll add 0. If it is B, I'll add 1, right? So I'll get, when I add 1 to ASCII value, I'll get B. So this is how I'll get all the characters one by one, and I'll process only those characters whose counts are greater than 0. So I traverse through this count array. So until E, I'll get all the zeros, A, B, C, D, all zeros. When I come to E, I'll print this character E, and when I'm at E, my index would be 4, right? So I'll add 4 to 97, I'll get the ASCII value of E, and I'll print E, and then I'll print its count value. So this way, I get all the characters in sorted order and their frequencies in big O of n time. This is how we create strings in Java. We will be covering Java string syntax in a separate video, right? And we get the character at a particular index using char function. In C++, we can access like a normal array. We can use array index operators to get the character at a given index. And when you use characters in a context where you should be using an integer, characters are automatically upgraded to integers. For example, I'm using characters as indexes here, right? So what happens here, it's automatically converted into an integer, and when conversion happens, its ASCII value is taken. So its ASCII value is taken, and then A's ASCII value is taken, and these are subtracted. Same thing happens in Java. Please remember, Java is UTF-16, but internal encoding is same as C++ ASCII values, because the first 128 characters have the same encoding. So this is one example. There are many examples based on string limited set size. For example, you can sort a string in big O of n time. You can use something like counting sort, and you can in fact use this code to sort a string. Now you have characters and frequencies. What all you need to do is, you need to print this character those many times and you get the sorted string, right? You print E 4 times, then F 1 time, then G 2 times, and this all can be done in big O of n time. Please note that this is only 26 loops, so this is a constant work, right? If you are doing this traversal, this is not considered as a linear time work. We are running only one traversal through the string and we are getting the sorted output, and we can in fact get the string sorted with one traversal. In this video, we have introduced a string data structure. We have talked about its speciality, that limited alphabet size or limited character size, and we have discussed one example problem. In the upcoming videos, we are going to talk more about a string and problems. Hi, in this video we are going to talk about strings in C++. So strings in C++ can be represented in two ways. One is an array of characters. So this way is called C style strings, and other way is using an object of string class, which is a better way, which is C++ style. Since C is kind of superset of C, so we have both ways to create a string in C++. So let's talk about the C style strings first. we create an array of characters. If you notice this declaration, you will see there is a difference. Generally we create arrays like this, right? This is what we expect. Here I have used a double quote, right, around a string. What happens when you use a double quote? Your compiler puts G first, then F first, then G, then it puts a special character \0. Right? Most of these C style functions, library functions, they rely on the fact that your string must be \0 terminated. When you are creating a string, you must guarantee that there is a \0. If you just use double quote, compiler automatically puts a \0. For example, strlen function in C style strings. How does it work? It basically finds the length of a string. And how does it find the length? It begins from the first character, checks if it's a \0 or not, goes to the next character, goes to the next character, and while it is going to the next character, it keeps on incrementing the count, and when it reaches the \0, it returns the count. That's the length of your string, right? That's how strlen function works. That's how most of the other C style functions also work. They rely on the fact that there is a \0 at the end of the string. Now what happens if I give more size here? If I say give size 6 here, then what will be the memory allocation? It will be 2 more cells with \0. This effect is same as your effect of integer arrays. If you initialize some elements, then rest of the initializer are zeros. Here they are initialized as \0. So the output of this program without this 6 is going to be GFG only. Even if you put, it's going to be GFG only, because C style string functions, the operations, whether you are printing them, whether you are calling a function on them, they all go this way. They begin from the first character, keep on printing the characters until they see a \0. So this cout str, it will print GFG. Please take a look at this program and try to guess the output. I created a character array or a string, C style string, and then I am calling size of str. So size of str, size of an array gives you size of an array. So what will you get here? You will get 4, considering that size of a character is 1 byte, because there is an extra \0 at the end. That is why you get 4, not 3 as output of this program. Let us take a look at this program. I have not used double quotes, so I am kind of creating a character array using single quotes. Here compiler does not put a \0. So if you go and print this character, if you run this program, you will get G, F, G, then you may get some characters, or you may get segmentation fault, or you may get GFG only. Why multiple possible outputs? Because that's how most of these C style strings are printed and worked. Your compiler, it will look at G, it will look at F, it will look at G, then it will search for \0. It will keep on printing the characters until it finds a \0. So if it might reach a memory which is not accessible to it, and then it might print segmentation fault, or it might print something like next character, whatever is there in memory, hash, $, and then it might stop at any point where it finds a \0. So if I'm using a character array with single quotes, I must put a \0 at the end if my plan is to use it as a string. If I'm going to print it, or I'm going to call any of these C style functions like strlen to find the length of it, or to do anything on it as a string, as a C style string, I must terminate it with \0. Or other option is I simply use double quote. Here compiler takes care of putting a \0 at the end. Let us now talk about functions used for C style strings. I'm going to talk about main 3 functions which are the most used. So the first one is strlen, which is used to find length of a string, and we have discussed an example of it. How does it work? You give it a character array, it will traverse the character array until it finds a \0 and counts the characters and returns that count. Next is strcmp. It compares two strings lexicographically, and if the first string is greater than the second string, then it returns a positive value. If they both are lexicographically same, if both the strings are same, then it returns 0. And if the first string is lexicographically smaller, then it returns a negative value. Let's do some examples of strcmpy. Let's take a look at this example.
ABC is lexicographically smaller than BCD. What do we mean by lexicographically smaller? The first string is A, if we are talking only lowercase alphabet, then AA, then there are more strings, all AA is, then AB is lexicographically greater than all these strings. And A, B, all strings one by one, A, B, A, B, A. Then AC is lexicographically greater than all these strings. So I think you got it right. When your character, which is appearing later in the sequence, appears first in a string, then this string is lexicographically greater. So we compare both the strings from the first character. As soon as we find a greater character in one of these strings, we say that this string is lexicographically greater. And if one string is A and other string is AA, then AA is obviously lexicographically greater because it has an extra character. So if I put ABC and BCD, ABC is lexicographically smaller, so I'll get the output as smaller. If I change the input, say I put here GFG, then I will get greater because GFG is greater than BCD. And if I put BCD, which means both the strings are same, then I'll get 0. Then I'll get 0 and my output will be same because both the strings are same. Before we talk about strcpy, let's take a look at this example. What is the problem with this program? This program will generate compiler error because it's an array of characters, and array of characters, if you use its name, then it gives you the address, but we can't use this on the left side of an expression because it's an array, right? We can't put a new value into this array. So this program will generate compiler error because of this line, right? I can't assign something to an address, right? I can't, and these strings are also string literals stored at constant locations in your program. So I can't assign one address to another address, which is not possible, which is like assigning an integer to another integer, like assigning 100 to 200, right? So this is not possible. So I cannot assign a string later is this way if I have created a string and did not initialize it at that time. So this is where strcpy comes into picture. I can replace this line with strcpy. So I pass str to it and I pass another string to this, and the other string, like any other C function, has to be null terminated. So this other string is copied to str, and this string is copied until there is a \0 in this string, right? So if I put GFG, I'm passing a string literal here, but we can pass another string also. I can have another string, say str1 equal to GFG, and pass str1 here. So what will happen now? Now this program works fine. I initialize the string and I copied GFG to it, and then I'm printing str, so I'll get GFG as an output. So you use strcpy to assign strings to an uninitialized character array. We just talked about C style strings. It is strongly recommended to use C++ strings over C style strings. The reasons are C++ strings have richer library. They support operations like plus, smaller than, greater than, equal to, smaller than equal to, greater than equal to. Remember what we had to do in C style strings. We had to use strcmp function to get these things checked, right, for two strings, which are possible with operators in C++ style strings. Plus operator, we can use plus operator to append one string to another string. In C style strings, there is a function called strcat that we have to use to append one string to other string. We can initialize a string empty and then assign the string later. We can do something like string str equal to str empty string, and then we can assign it later. Remember what we had to do in C style strings. We had to do strcpy to initialize an empty string and then copy one string to other, right? We do not have to worry about size of a C++ string. In C style strings, you need to initialize a string because they are character arrays. So you need to, put some size and then initialize those strings. This difference is same as an integer array versus an integer vector. C++ strings are like vectors. They are contiguous in memory location. So they have this advantage of cache friendliness, and then they are allowed to have dynamic size. You can push as many characters as you want. Last point, whenever you need a C style string, whenever you need a character array, you can use a function C_str to convert a C++ style string to a C style string. So in this example, I have created a string and I have discussed some commonly used functions which are there in string class. So I create a string object this way. Please remember, string is a class in C++. So we are going to discuss classes later in this course, but to give you an idea, a class is something which has data members and functions, and typically data members are accessed through functions. So when we call functions of a class using dot operator, and there's something called object also. Object is a variable of that class, like integer variables, float variables. We have objects of these classes. We are going to talk about these things in detail, but for now we can understand there's something like class which has functions, and class is a data type. Variables of this class are objects. So string is a class. I created an object of it here and I'm using functions on this object. So this will give me details of this object. So length function will give me the length of the string. Plus operator, it concatenates xyz to this string. So if I concatenate xyz to it, I'll get the length of the string with xyz concatenated. So first length function will give me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And if I append xyz, now the length becomes 13 plus 3, 16. Right? And I'll get GeeksforGeeks xyz if I print str here. Substr function, it gives you substring, and the parameters, the two parameters that it takes are beginning index and length of the substring you want to find. So this gives you substring beginning with index 1, which is E, and length 3, so it will give you EEK. If I pass 2 and 4, then what it will give? It will consider the string beginning from this E and length 4, so EKSF. That will be the output if I pass 2 and 4 to this function substr. Find function, it is used to search a string in a given string. So if I call str.find and if I pass EEK, I will find index of EEK if it is present in the string. Since EEK is present 2 times in this, the find function returns the index of first occurrence. So here I'll get the index of first occurrence, which is 1. So the output of find will be 1 here. What if the string is not present? Then find function returns a special constant called a string : pause, which is string : n pause, which is used to indicate no position found for this string in the given string. So the output of this program is 13, then GeeksforGeeks xyz, then EEK, then 1 index of EEK in this string. Let us take a look at this program. Here I have used operators instead of strcmp function that we used in C style strings, and they are very convenient to use. I am writing s1 equal to s2. If they are same, then this condition will become true and it will work like strcmp. It will compare character by character. Here output will be greater because BCD is lexicographically greater than ABC. So the output for this program is greater. Let us now talk about reading in strings from console. Let's take a look at this program. I have created a string, then I am asking user to enter name. I am doing C in str and then I am printing the name. This program, if I enter the name as Sandeep, when it prompts me to enter the name, and if I run this program, I'll get the output as your name is Sandeep. Now if I enter Sandeep Jain, then this program would print only Sandeep, because the CIN operator, when it sees a space, it stops reading the character when it sees a space or a new line character. So how do we read strings with spaces? How do we assign Sandeep Jain to this string after reading it? So we don't use CIN for this purpose. We have a different function for reading a string. We have this function called getLine. This function receives input string cin as first parameter, your string as second parameter. Now if I run this program and if I enter my name separated by space, Sandeep space Jain, and then I'll get the output as your name is Sandeep space Jain, because this get line does not stop reading until you press the enter key, right? So this get line has one more optional parameter which you can specify to specify the character after which to stop. For example, instead of new line, you can specify a character that please stop when you read A as input, right? So if it sees an A, it will stop. By default, it stops when it sees a new line character. Let us now talk about iterating through a string. So C++ style strings can be iterated this way. I can find the length and then I can run a loop for I equal to 0 to str.length and I can print stri. Please remember, like vectors, C++ style strings can also be accessed using index. I can put an index and get the ith character. So this is one way of traversing. This is another way, using for each loop. I can use colon and I can access all the elements of the string one by one using this for each loop. So in this video, we talked about C style strings, we talked about C++ style strings, we talked about functions, and then we talked about reading a string, and then we talked about traversing through a string. Please remember, it is strongly recommended to use C++ style strings over C strings. Let's not use C strings because they are very much troublesome. We have to ensure many places that we are putting a \0. We have to take care of the size, right? C++ style strings are dynamic in nature. Functions in C++ style strings are very easy to use compared to functions written in C style strings. For example, to do a concatenation, we can just call plus. To do comparison, we can use smaller than, greater than. Also, the functionalities are much richer in C++ style strings. All these functionalities are not there in C style strings. If we talk about all the functionalities of C++ string, there is a big list. We can do many things with this class. There are plenty of functions available in it. So please stop using C style strings and use C++ strings wherever possible.
Hi, in this video we are going to talk about a string in Java. A string is a sequence of characters, and in Java every character is stored using 16 bits. Java uses UTF-16 encoding for storing the characters. There are 4 ways to create strings in Java. One is normal character array. We just make an array and initialize it with some characters, or we can make an array using new keyword and then assign values to the individual elements of this array. This is one way. We can also use array list of characters. Then there are 3 classes: string, string buffer, and string builder. The advantage of these 3 over normal character array is these classes have many string specific functions. Like you can search a substring in a given string. You can find first occurrence of the substring. You can find last occurrence of the first given substring. You can quickly concatenate another string. There are plenty of functions which are available in these classes. Now, why do we have 3 classes? Why not only one string class? The reason is this creates an immutable string. The string class objects that we create, they are immutable. Immutable means the content of the string cannot be changed. Once you create a string geeks, like an array, you cannot change this character to something else. If you wish to change this character, you need to create a new object. All these string class functions like concat, toUpper, toLower, they return a new object when you call those functions on a string. They don't modify the existing object because this string class objects, they are not mutable at all. So if you want to modify the string, then you have 2 mutable classes which allow string objects to be modified. The 2 classes are string buffer and string builder. Now the question arises, why do we have 2 classes for mutable strings? The first class, string buffer class, is a thread safe class. We can use it when we have multi-threaded environment and we have the shared object of string buffer being used by multiple threads. A string builder is not thread safe. It's used only within a thread. Now, why do we care about a class which is not thread safe? The reason is when you create a thread safe class, that involves extra overhead as well. That extra overhead is not there in string builder. So if you are writing a single threaded program which requires mutable strings, then you will use a string builder. If you are writing a multi-threaded program that requires mutable strings, then you will use a string buffer. And if you need immutable strings, then you will use a string class. Please note that string objects are immutable. They cannot be modified. So thread safety is not required. They are automatically thread safe. You need thread safety when one thread is modifying this particular object and other thread does not get the latest updated object, or they try to modify it at the same time. So string class is automatically thread safe. In this video, we are going to focus important functions on string class. Our focus is going to be only on the string class here. Here is first example program of the string class. We have created a string geeks and str is a reference to this string and this is an immutable string. We can't modify it. Now here are functions of the string class, ready-made functions available to us. Length is a function that returns how many characters the string has. So if the string is geeks, we are going to get the length as 5, 1, 2, 3, 4, 5. Char at is a function that gives you the character at a given index. So I pass the index as 3, so I'm going to get the character at index 3, 0, 1, 2, 3. So I get k. If you are coming from a C or C++ programming world, this might be surprising for you because in C and C++, we can get the character at a given index using square brackets, but that's not allowed in Java. In Java, you can only get the character at a given index using char at function. One more thing, you can't use this caret on the left side. For example, you can't do something like this, str.char at 3 equal to some character a. It's not allowed because it's immutable and caret simply returns a character, not a left side value, right, that you can assign. So this is not allowed. We can only use caret on the right side of an expression or to get the value at an index, right? We can't use it to assign value at an index. Substring function. So substring function is also different from C++ if you're coming from C++. Here substring function can be called two ways. The first way, when you call it, you pass only one parameter, and this is how the substring function works. It takes that parameter as an index and it returns a substring which contains the character at this index and all the other characters on the right of it. So I passed the first parameter or the only parameter as 2, so I'm going to get the substring as EKS. That's the output of substring when you pass a single parameter. Now when you pass two parameters, it considers the second parameter as an end index. And this is how it works. Start index is included, right, and end index is not included. So when you pass substring function like this, 2 and 5, characters from start to end -1 are returned, right? So the substring from 2, 3, 4 and before 5, so it's going to return EKS, right? The output is EKS. Now if I change this parameter to 4, what will be the output? Can you guess? The output is going to be characters from index 2 to 3, which means 2 characters only because this index is not included. So we are going to get the output as EK. Here is one interesting fact about Java string objects. When you create string objects using literals, your Java compiler does not allocate new memory for the literals if they have same content. For example, the string s1 has content geeks and the string s2 has content geeks, and they are immutable. So compiler does this memory optimization. It does not allocate a new memory for the same string content. What happens here is both S1 and S2, they refer to the same content geeks. So if you compare S1 and S2, S1 and S2 are two references, right? So when you compare them, references are compared, not the content. To compare contents of two strings, we have separate functions like equals to and compare. This double equal to compares whether two references refer to the same object or not. And surprisingly, we get the answer yes here. Even if we created two variables separately, two reference variables separately, they refer to the same string constant. And this is called a string literal pool in Java. Now, if you create a string using new keyword, then it creates a new memory for geeks. So this S3 refers to a new object. When you use a new keyword, a new string object is created and S3 refers to this. So when you now call S1 and S3, you get the answer as no. They don't refer to the same object. So this is an interesting fact about Java string constant literals. Let us now talk about more functions on the string class. The first function is contains function. Contains function takes a string as an argument S2 and it is called on an object S1. It returns true if S2 is present in S1 as a substring. Now here S1 is GeeksforGeeks and S2 is geeks. So geeks is present inside the string, so our output is going to be true. So this function is going to return true and we are going to see true on the screen. Now say if I change this string, I change this S to Y geeky, now output is going to be false because it's not present as a substring in this string, right? And this string can be present anywhere. For example, if I pass for here, right, then also I'm going to get the output as true because for is present at this index. So my output is going to be true. So this is contains function. Here is one more function, equals function. Equals function returns true if the content of both the strings S1 and S2 are same, and they're not same, then it returns false. Here our first string is GeeksforGeeks and our second string is also GeeksforGeeks, so it's going to return true. If I make any change in any of these two strings, I am going to get the output as false. So it simply checks character by character if they are same or not. Let's now see the compare to function. Compare to function compares S1 and S2 lexicographically, and if they are exactly same, then it returns a 0 value. If S1 is lexicographically greater, then it returns a positive value, and if S1 is lexicographically smaller, then it returns a negative value. So compare to can be used in place of equals as well. Equals is simply used to check whether they are equal or not, and if we wish to know whether they are equal or not and which one is lexicographically greater, then we use compare to. So here in this example, S1 is GeeksforGeeks and S2 is FOR, and you can notice that this one is lexicographically greater because G comes after F. So we are going to get the output as S1 greater. Now if I replace S2 with GeeksforGeeks, I'll get same as output. And if I replace say the second string with something like her, then H comes after G, so I'm going to get S1 is smaller as output. If I change this code to HER, H comes after G, so I'm going to get the output as S1 is smaller. Let's now talk about the next function, index of. It's an extension of contains function, like compare to is an extension of equals function. First two functions are Boolean and these two functions return integer value. So index of function returns a negative value if string S2 is not present in S1, right? Contains function returns a Boolean value, true or false. If present, then return true. If not present, then return false. Index of function returns a negative value if S2 is not present. Otherwise, it returns index of first occurrence of S2 in S1. So if you see this string S2 geeks and S1 GeeksforGeeks, this is present at index 0. This is where the first occurrence is. So index of is going to give you 0. Now if I pass the string as FOR, then output is going to be index of FOR in this. So I'm going to get 0, 1, 2, 3, 4, 5. So the output is going to be 5. Now if I pass a string which is not present, say I pass GOR, then I'm going to get a negative value. My output is going to be a negative value, right? Now, one more thing about this index of function, if it can receive one more parameter. If I want to know if a substring is present after a given index or not. Suppose I know that geeks is present at the index 0. I want to know whether it is present after index 0 or not. So it receives one more parameter. I can pass 1 as the other parameter, and now it will start searching from here, and it will not return the index, the occurrence this one, because I have passed 1. So I am telling this function to search from here, and it's going to return this index. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to get the output as 8 now because I passed another parameter. So index of function can be used to find the first index or first index from a given index. Index of returns first index. There is another function called last index of that returns last index of the string if it is present in the given string. Let us now take a look at this program and try to guess the output of it. You may pause this video now. The output of this program is geeks for geeks and then false. Let's see how does this program work. So we create a string s1 which is creating a literal in memory geeks. We have a reference of this in s1. Now we are creating another reference to this s2. So s2 is another reference to this literal. Now what are we doing? We are saying s1 is equal to s1 plus for geeks, or we are saying s1 is equal to s1 dot concat for geeks. Now this is where a string becomes interesting. Since a string are immutable, so when you concatenate something to a string, it creates a new object, right? And s1 starts referring to that object instead of modifying the same object. So what happens now is there is one more object created, geeks for geeks, with the new content of appended string. New object is created, new string object is created, and then this s1 start referring to this new object. That's what happens when you call this line. It does not modify the existing object because it's an immutable thing. When you are appending something, this thing is appended to this and a new object is created. So now when you print s1, you will get the output geeks for geeks as expected, but this might be surprising because s2 was initialized as s1, but now when I'm checking whether s1 and s2 are same, they are referring to the same object or not, I get the output as false because this line changed the reference. It changed the reference to refer to this new object from here, right? So that's why we get the output as false. Let us talk about this simple string problem. We are given a string. We need to check whether the given string is palindrome or not. A string is called palindrome if you read it from left to right and also read it from right to left. You read the same string. For example, if you read this string from left to right, A, B, C, D, C, B, A, and if you read from right to left, A, B, C, D, C, B, A, same string. So it's a palindrome. Let's now see this string. If you read from left to right, A, B, B, A, and if you read from right to left, A, B, B, A, palindrome. Now if you see this string, if you read it from left to right, you get G, E, E, K, S. Right? If you read it from right to left, it's not G, E, E, K, S, right? It's from S, K, E, E, G. So they are not same. So this string is not palindrome and these two strings are palindrome. Now please pause this video and try to write down a function that takes a string as an argument. This function returns true if the given string is palindrome, otherwise returns false. Let us first talk about a naive method to solve the problem. The idea of naive method is simple. We take the input string, then we get reverse of the string. We reverse the string and store the reverse in a different string. So we have two strings, input string and reverse of it. Now what we do is we compare the input string with reverse of it, and if they are same, we return true, otherwise we return false. Now please pause this video and try to implement this approach. Let us now see implementation of the naive method. Here is C++ implementation and this side we have Java implementation. In C++, objects of a string class are mutable and we have reverse function which we can apply on a string. The reverse function takes two iterators. So I passed begin iterator and end iterator, and the content between these iterators is reversed. So I will pass strings. So first I've copied the given string to the reverse, and then I have passed the begin iterator of reverse and end iterator of reverse. So this function reverses this string rev, right? And after rev is reversed, we need to check whether rev is equal to str or not. If rev and str are same, then this is going to return true, otherwise it's going to return false. Please note that in C++, when you use double equal to operator, it compares contents of both these strings. It's overloaded in the string class. Let's now see the Java implementation. In Java implementation, string is immutable. So what I've done here is I have created a string builder object, which is mutable, right? So we create a string builder, we call it rev, and we create the string builder using the given string. So it has the same content as the given string. Now the string builder is mutable and has a function called reverse. So we reverse this string builder object, and now all we need to do is we need to compare this rev with str. So we call str.equals and we compare it with the string equivalent of the string builder. So we call toString function on the string builder object. So we get a string here and we had our input string. These two strings are compared and we check whether they are same or not. So this is how we check in both C++ and Java. Let us now analyze the solutions. In both the solutions, we are creating a copy of the string, right? We are creating a reverse string here and we are creating a reverse string builder here. And this requires auxiliary space, right? And then we are comparing reverse and the original string one by one. So it's going to take theta n time, because you will always do the reverse. Whatever string you are provided, you are always going to traverse through the whole string and then you are going to reverse it, right? Also, it requires theta n auxiliary space. So theta n time and theta n auxiliary space, right? And this is how it works. You are given a string, you reverse it, right? And you compare string and reverse. And this much is the time and auxiliary space required by the solution. Now please pause this video and think of a solution that works with theta 1 auxiliary space and is big O of n. So it might work in constant time in some cases, and n is an upper bound, not the exact bound. Here it is theta n. So the solution that I am going to talk about is better, because in the worst case it will take n, and in the best case it will take constant time, and it takes constant extra space. Let us now talk about the efficient solution. The idea of the efficient solution is first compare first and last characters. For example, if this is a string, you compare this character with this character. And if these characters are not same, then your string cannot be palindrome. And if these characters are same, then you go ahead and compare these two characters. You mainly begin two indexes. One starts with the left side and the other starts from the right side. You compare the characters at the begin index and the end index. If they are same, then you move ahead the begin index and you decrease the end index. So now your next characters are these two. If they match, fine, otherwise return false. And if they match, then what are you going to do? We are again going to move these begin and end index one position ahead. So begin also comes here and end also comes here. And begin and end, when they become same, it means you have one character left. So you can return true. Now there might be one other case when begin and end do not become same, and that other case would be in case of even sized strings. Let's take an example of even sized strings. Let's say our string is CBA. Now we'll again begin from this side and we'll begin from this side. We'll compare begin and end, they are same, so we'll come here. Right? Now we'll compare begin and end, they are same, so we'll come here. Now we'll again compare begin and end, right? This is our begin and this is our end. They are same, so we'll move ahead. Now what will happen when you move ahead? Your end is going to come here and begin is going to come here. So when begin and end cross, then you also return true, right? That's the simple idea. Now please pause this video and try to implement this idea. Let us now see implementation of the efficient approach. So I've written a function isPal in Java and isPal in C++. We pass a string argument. In Java, it's by default by reference. In C++, I've used ampersand to pass by reference, because if I don't pass by reference, then a string will be copied. That would cause unnecessary copying of the strings. So once we receive the string as an argument, we initialize our begin with 0 and end with last index, and last index is string length -1. Now we run a loop, and this loop runs while begin is smaller than end. See, if begin becomes equal to end, then your string is odd length string and you've reached the middle character, you should return true, right? So we come out of the loop and we return true. And if begin and end, they cross each other, then also you have traversed through the whole string, you matched every character, you come out of the loop because begin and end they cross, and you will return true. Now what do we do inside the loop? We compare the character at the begin index and at the end index. If they are not same, then we return false immediately. So we start traversing from both the ends. If they are not same, we return false. If same, then move ahead. To move ahead, we do begin plus plus and end minus minus. And we again compare. If they are not same, then return false. If same, then move ahead, move ahead, move ahead. If it's an odd length string, then begin and end would become same, and you will come out of the loop and you will return true. If this is an odd length string, then begin and end will keep on moving toward, and if the string is palindrome, then they will reach the same character, middle character. You will come out of the loop and you will return true. And if it's an even length string and if it's a palindrome, then begin and end cross each other and you will return true. Now what is the time complexity of the solution? We are traversing from both the sides, so every character is being compared at most once, right? If it's not a palindrome and if say corner characters are themselves not matching, then it's going to return in big O one time, constant time. And in the worst case, when the string is palindrome, then every character is being compared at most once. So it's theta n in the worst case and theta 1 or constant in the best case. And in general, we can say it's a big O of n algorithm. Big O of n covers both worst case and best case. Worst case is theta n and best case is theta 1. And how much auxiliary space it requires? It requires constant extra space. So we can say big O of 1 or theta 1. See, constant can be represented by either big O of 1 or theta 1. And when we write big O of n, it means it's upper bounded by n. It can take less time, and that's the situation here. This program might end with constant time if the last two characters themselves do not match. Let us talk about this problem. We are given two strings S1 and S2. Our task is to find out whether string S2 is a subsequence of S1 or not. We are going to return a boolean value. We will return true if S2 is a subsequence, otherwise we will return false. Let us first quickly define what is a subsequence. A subsequence of a string is obtained by removing 0 or more characters. And whatever characters we pick, the characters that we don't remove, we need to put those characters in the same order as they appear in the original string. Let's understand with this example. ABC, its subsequences are empty string. We have removed all the three characters. A, we have removed BC. B, we have removed AC. C, we have removed A and D. AB, we have removed C. But A and B should be put in the same order. Please note that BA is not a subsequence. AB is a subsequence. AC is a subsequence. We have removed B. And this is where we note the difference between subsequence and substring. Substring means contiguous characters, right? Here we don't need to have contiguous characters. We may remove characters from the middle. BC is a subsequence, we have removed A. ABC is a subsequence, we have not removed anything. The total number of subsequences in a string of length n are going to be 2 raised to the power n, right? You can notice that if you have a string of length 3, then there are 8 subsequences. And the reason is simple. For every character, you have two choices. Either you keep it or you don't keep it, right? That's how you are going to get 2 raised to the power n subsequences. Now, please pause this video. Try to write down a function that takes a string S1 and another string S2, returns a boolean value, returns true if S2 is a subsequence of S1, otherwise returns false. So now we understand subsequences. Let's take a look at the examples. In this example, ABCD is our S1 and S2 is AD. AD is a subsequence of ABCD. We have simply removed BC. Now if we see this example and this example, AED is not a subsequence. See, if you remove BC, the order that you get is ADE, but we have the order here AED. So AED is not a subsequence. The characters should be in the same order, right? So now please pause this video and try to write down a function that takes two strings as input, S1 and S2, and returns true if S2 is a subsequence of S1. A naive solution to solve this problem is to generate all subsequences of string S1. There are going to be 2 raised to the power n subsequences, and then for every subsequence compare it with S2 and see if any subsequence matches. As soon as you find a subsequence matching with S2, you return true. The time complexity of this naive solution is going to be clearly upper bounded by 2 raised to the power n into n. See, n is the length of the larger string, and since I'm using big O upper bound, I can use n here as well. Although we are going to compare the smaller string with every subsequence. If you want to be more precise, you can put the length of smaller string. So this time complexity is actually exponential, and we can do much better than this. Please pause this video and try to think of a better solution. Let us now talk about idea for the solution. We are going to use 2 index variables I and j for both these strings. And now what we are simply going to do is we are going to compare s1i with s2j. If the 2 characters match, then what you will do, you must have guessed it, you will move ahead in both these strings. Because we have matched this character, we have found this character in s1 in the same order as it should be in the s2. Right? And if they do not match, then what we do is we simply move ahead in the S1, because this character is of no use for us. See, it might be appearing somewhere later, but we are looking for the character R now after we have matched G, right? As long as we don't find R, we would not process any other character, right? Because the order of characters in the subsequence should also be same. So we begin with GG, they both match, right? So we are going to move ahead in both these strings. We are going to come to E here, and we are going to come to this R. Now these two are not matching, right? Although E is required here in S2, but we are looking for R now, right? So we'll move ahead in this string. Now E and R again not matching, so we'll move ahead. We'll keep on moving ahead and we'll stop at this point, right? So we kept our J here and moved I to this point. Now they both are matching. Now we'll move ahead in this string. Now we'll compare and we also move ahead in this string. We have I++ and J++. Now we'll compare G and G, again matching, so we'll move ahead in both these strings. We'll come here and we'll come here, right? And we'll compare E and D. E and D are matching now, so we'll move ahead in both these strings. So we come to S here and we come to this E here. Now we compare S and D, they are not matching, so we'll move ahead only in this string. Now again not matching, so we'll move ahead in this string, we'll come here. Now they both matched, right? So we move ahead in both these strings. And when we reach end of these strings, in any of the 2 strings, we stop our running the loop, right? And if you have reached end of S2 also, that means you have found all the characters in the same order in S1, you will return true in this case. But if you have only reached end of S1 without reaching end of S2, right, then you will return false. Now you have complete idea about the logic, intermediate steps inside the loop. Please pause this video and write down the solution yourself. Please write down both iterative and recursive solutions. We are first going to write down an iterative solution, then we'll discuss a recursive solution. Let's now take a look at our iterative implementation. We have 2 variables j and I. J is for indexing S2 and I is for indexing S1. And the code written here is close to C++ style. In Java, you can simply use boolean instead of bool. Also, if you're programming in Java, you need to use capital S here for string. And if you're programming in C++, then you can slightly optimize it by passing it as a reference, right? This will avoid copying of S1 and S2 when we pass them into a function, right? And in C++, it's again a better programming style to use const also, right? When our function's intention is to never modify the string, right? So we can use ampersand and const both in the function if you are programming in C++, right? And if you are programming in Java, we simply need to use capital S and boolean here. So we begin with j equal to 0 in second string, and we begin with I equal to 0 in the first string. So instead of using a while loop, I have used a for loop here because I is always going to be incremented, right? The conditions that we wrote, I was always being incremented, right? So we are simply traversing through string S1, and we have this condition that we should not reach end of S2 also, because we are going to compare S1i with S2j. If they are matching, we are simply doing j++, and we are always doing I++. And at the end, I have written some short codes. I have avoided if else condition. This line means if j is equal to m, then return true, otherwise return false. So that's the simple idea. You run a loop for this string, right, s1. You have index j for this string. If I and j are matching, then you do I plus j plus plus, and I is always incremented. So a and a matching, we do j equal to 1. I is incremented to 1. Right, so this 1 and this 1, they are not matching, so we'll do simply I plus plus. I will come here. C and D not matching, so we'll do I plus plus. Now these two are matching, so we'll do I plus plus and j plus plus. J will become 2. Now again they are matching, so we'll do I plus plus and j plus plus. J now becomes 3, right? So j is now equal to m, so we'll come out of the loop because this condition becomes false, and j is equal to m, so we'll return true also. Now talking about the time complexity of this iterative solution, this solution is clearly big O of m plus n, and auxiliary space required is big O of 1. See, why am I saying big O of n plus m? Somebody can pass a larger s2. In that case also, it's going to run this loop, right? And we can do slight optimization in this solution. For that particular case, we can have a condition if n is smaller than m, then we can immediately return false. That's an optimization for some cases, right, where your string length s1 is smaller, right, because if this s1 is smaller, then s2 cannot be a subsequence of it. So this is our iterative solution. Now please pause this video and try to write down a recursive solution. See, a recursive solution is not going to be better than this. It's just a recursion exercise for which I am asking for you to write this recursive solution, and I am also going to write the recursive solution. Although iterative is better, recursive is going to cause extra space and extra overhead. Here is a recursive solution, and in the recursive solution, we are matching last characters instead of first characters. I am matching n-1 and m-1th characters. See, if you match first characters, that solution will also work. But if you try writing that solution, then you will have to get the lengths first, or you will have to pass 2 extra parameters for indexes, right? Here we are already passing lengths of the strings. So using the lengths, we can always get the last characters, and we can pass updated lengths in every iteration. That's why we are matching with the last characters, and that's generally recommended practice for recursive solutions of strings or arrays. We begin from the end so that we can use the length itself as an index, and we can keep changing the length. So n and m are passed, and we are comparing the last characters, and the last characters are matching. We are calling for n-1 and m-1 like the iterative solution. And if they are not matching, then we are recursively calling for n-1 and m. It's again similar to iterative solution. And here are the base cases. When you are reducing n and m, one of them can become 0. So if m becomes 0, it means your other string, the smaller string, has finished. So you have found all the characters of it in the bigger string in the same order. So you return true in this case. And if n becomes 0, it means you could not find all the characters of second string in the first string, and your first string finished, so you return false. See, the order is important. If I put n equal to 0 at the top, then it might give you incorrect results. For example, it will give you incorrect results for this example itself. Both of them become 0 here, and we should be returning true. So let's take a look at the dry run that we have written here. A, B, C and AC are 2 strings. 3 is the length of first string, 2 is the length of the other string. So we compare the last characters. We reduce n and m by 1, so we have 2 and 1. Now we compare the last characters at n-1 and m-1, which means we compare B and A. They do not match, so we reduced n only, we don't change m. Now we compare A and A, they are matching, so we reduce both of them, right? And now we have 0 for n and m both, but we check for this condition first and we return true. So this function call is going to return true its parent, and its parent is going to return whatever the called function return, and the parent is also going to do the same thing. So we get true from here, right? And this also returns whatever this returns, so it's going to return true. And this also going to return whatever its parent return, its child returns, so it's going to return true. And it's also going to return true to the main caller. So this way we get the output as true. And again, please note that if you're implementing it in C++, then please use ampersand here for optimization, and for better programming use const also in both the places, ampersand const. And in Java, we need to use boolean here. We need to use capital S here. Also, indexes characters at indexes n-1 and m-1 are not accessed this way in Java. I forgot to tell in iterative solution. In Java, we need to use char at, right? This is the syntax in Java. We call a function char at on these strings to get the character at index n-1. Similarly, we need to use char at here. Now, talking about the time complexity solution, it's same as the iterative solution, just that we have written a recursive solution. So time complexity is big O of m plus n. In fact, auxiliary space is also m plus n here, and this is where it's not good as the iterative solution, right? Iterative solution requires big O of one auxiliary space. Here we have recursive calls, so we need big O of m plus n auxiliary space for function call stack. Let us talk about this problem. We are given two strings. We need to check if these two strings are anagram of each other or not. Anagram is basically checking whether two strings are permutations of each other or not, which means every character that appears in the first string should also appear in the second string, and the frequency of every character should also be same in both these strings. However, the order of appearance may differ. Let's understand the problem with these examples. Here we have a string LISTEN and the other string is SILENT. All the characters which are here, they are also here. L is here, I is here, S is here, T is here, and N is also here. So our output is yes. If you see this string, A appears 3 times here, A appears 3 times here as well. C appears here, C appears here, B appears here, B appears here. So it's an anagram. Now if you see these two strings, here A and B both are present in both these strings, but A comes here 2 times and A comes here 1 time. B comes here 1 time and B comes here 2 times. So these are not anagram of each other. Now please pause this video and try to write down a function that takes 2 strings as arguments and returns true if these 2 strings are anagram of each other, otherwise returns false. Let us first talk about a naive method to solve the problem. The idea is simple. We first sort both these strings. After we have sorted both these strings, and if they are anagram, then they should become same, right? Because the smallest character will come first with all its frequencies, then the greater character, then the greater character, and at the end we'll have greatest character with all its frequencies. So let's understand the approach with this example. Let's say we have first string as A, B, AAC, other string as AA, CBA. After sorting, our first string becomes AAABC. And our second string becomes AAABC. Now what all we need to check is if they are same or not, right? If they are same, we return true, otherwise we return false. A quick check that we have added at the top of this implementation or this implementation in Java is comparing lengths of both these strings. If lengths of both these strings are not same, then we immediately return false. Then we don't need to sort them and then compare. So first we compare the lengths. If lengths are not same, then we immediately return. Otherwise, we sort them and then compare. So in C++, you can compare 2 strings contained by putting a double equal sign. In Java, if you want to compare 2 strings and if you put double equal sign, this is going to compare the references, not the content. In Java, we have a function called equals that compares 2 strings. And C++ has a very simple code to sort a string. In Java, this is one way of sorting, but there is no direct method to sort a string, no function in the string class. So what we do is we convert this into an array, then call array.sort. It's arrays.sort. We call arrays.sort. Arrays is a class in Java which does all the standard arrays functions like binary search and sorting. And then we create a string from the sorted array, right? So we create the string S1, we create the string S2. And if S1 and S2 are same, then we return true, otherwise we return false. Let's now talk about time complexity in this solution. This solution clearly requires big O of n log n time because sort function takes n log n. However, you can implement the sort function or your own sort function for strings to work in big O of n time because the alphabet size is small. You can count the frequencies and then sort the strings in big O of n time. There is actually a better method than sorting, right? This method is going to traverse both these strings only once and it's going to tell you whether they are anagram or not. please pause this video and think of an approach that works with one traversal of both these strings and returns true if the strings are anagram, otherwise false. Let us now talk about the efficient solution. The idea is a standard character counting technique for strings. We use characters as indexes in a count array. We have a count array of size 256 here. If you have lowercase alphabets only, then you can make a count array of 26 as well, right? And then you can use character value minus a as an index. So what we do is we initialize a count array. For every character in string 1, we increment the count. For every character in string 2, we decrement the count. And if two strings are anagram, then finally your count array should become 0. It's like counting frequencies of all the characters in string 1 and counting frequencies of all the characters in string 2 and then comparing both of them. So instead of using two count arrays, in this implementation, we have used a one count array. So we create a count array of size 256 here. Char is a constant here, a static final variable here in Java. And what we do is we traverse through both the strings and we use characters as indexes. For every character in string 1, we increment the count. For every character in string 2, we decrement the count. And finally, we check if this count array is having all 0 values or not. If we find a non-zero value, it means they are not anagram. Let's understand the solution with this example. Let's say we have this string and this string. We initially have count array as 0. Now we traverse through all the characters of both the strings. So we traverse through first characters. We increment the count when we go through this character here. Then we come to this character, so we decrement the count. It becomes 0. Now we come to this A. We increment the count. We make it 1. When we come to this C, we decrement the count. We make it -1. B, increment the count for first string character and decrement the count for second string character. Now C, increment the count, so it becomes 0. B, decrement the count, becomes 0. Now A, increment the count and A, decrement the count. So finally you have 0. After the loop, if there are anagram, there should be 0. And if there is any mismatch in the frequencies or characters, you will have a non-zero value. You will have an either negative value or positive value. So this is how the solution works. We are basically comparing frequencies of characters in both the arrays, both the strings. Now what is the time complexity of the solution? We have a count array of constant size, assuming that alphabet size is a constant. So I am not going to consider this loop as part of the time complexity. If you see otherwise, we are simply running one loop to traverse both the strings. So if n is the length of both the strings, then the time complexity is big O of n. Now, if we consider this also alphabet size also, then we can say big O of n plus char, where char is the alphabet size. And how much auxiliary space this solution requires? This requires big O of char auxiliary space. So this solution works in linear time, does one traversal and checks whether two strings are anagram or not. Let us talk about this problem. We are given a string with possible repetitions. We need to find out leftmost character that repeats. So let's begin with the second example. In this example, we have A, B, B, C, C. So you can notice that B is the leftmost character that repeats. So our output is index of B. Index of these characters are 0, 1, 2, 3, 4. So we return 1. Now in this example, you can notice that G is the character that repeats here, E also repeats. But we need to consider the character whose first occurrence is leftmost, right? So E repeats first, right? You can notice that E's both occurrences appear first before the two occurrences of G, but G's first occurrence is leftmost, right? So we are talking about first occurrence here, right? That's why our output is G, index of G, 0. 0 is index of G, so we output 0. Let's now see this example. Here all the characters are distinct, so there are no repetitions. So our output is -1. Let me ask you a quick question. Let's say your string is A, B, C, C, B. Then what will be the output for this one? It should be index of B, because B has leftmost occurrence and B is a repeating character, right? So our output should be 1 for this input string. Now please pause this video and try to write down a function that takes a string as an argument and returns index of leftmost occurring character. If they are all distinct, then it returns -1. Let us first talk about the naive solution to solve the problem. The naive solution is we traverse through every character, and for every character we check if it repeats, right? We start from here and then compare it with all the characters after it, and if it repeats, we return it. So we run two loops. This is C++ implementation and this is Java implementation. In both the implementations, we are running two loops. In the outer loop, we are running a loop from first character to last character. In the inner loop, we are running a loop from the next character to the last character, and we are checking if the first character is matching with any of the upcoming characters. So we begin with C and we run a loop from j equal to I+1. It doesn't match with any of the upcoming characters. So then we run a loop for this character and we find a match for this j. So we return index of A, which is 1. Now, what is the time complexity of the solution? This has two loops. So time complexity is clearly big O of n square. Please note that I am using big O notation because in the best case, it might find the first character itself as repeating and returns in constant time, or might take linear time also in some cases. But worst case is big O of n square, and worst case will happen when all the characters are distinct, right? You will take theta n square time in that case. Now please pause this video and think of a linear time worst case approach. Let us now talk about a better solution to solve the problem. This solution is based on the simple typical trick of strings. We use characters as indexes and we store their frequencies. So we do two traversals of our input string. In the first traversal, we store counts or frequencies of all the characters. In the second traversal, we check which is the first character which is having frequency more than 1. So let's understand the solution of this example. Let's say we have this string A, B, C, C, B, D. We traverse through the string and increment count of every character in this count array. The size of this count array is 256, assuming that our input characters are from ASCII. If your characters are lowercase English alphabet, then you can reduce the size to 26 and you can shift the indexes of characters by subtracting ASCII value of A. Here we are assuming 256. So we initialize the count array as 0, and after initializing the count array, we traverse through the input string and increment count of every character. So this is our count array after first traversal, right? This is Java code here, right? And please note that in C++, we have initialized the count array as 0. In Java, when you create an integer array, it's by default initialized as 0. Now we do one more traversal of the input string. And for character at index 0, which is A, we use A as an index and see what is its count. Its count is 1. Now we use character at index 1, which is B, as an index in this array, and its count is 2. So we find a character whose count is more than 1. So we return index of this character, which is 1, as an output. So two loops, one loop to count frequencies, other loop to find the first character. So this solution works in linear time but requires two loops of our input string. Now please pause this video and try to think of a solution that finds leftmost repeating character in one traversal. Let us now see efficient implementation. The idea of this efficient implementation is to traverse the string from left to right and keep track of index of first occurrence of every character. And we use our standard trick of strings here. The standard trick is to use characters as indexes. So what we do here is we create an array to store the first indexes of the characters, and the size of this array is 256 because we are assuming that our character set size is 256 ASCII values. We fill this array with -1. -1 means that none of these characters have seen so far, right? So if you have this string, for example, you create an array as -1 values and you initialize your result as infinite. Now what you do is you traverse through the string, you begin with A, you see that A is not seen already, and how do you figure out? You use A as an index in this F index array, and if it's -1, that means its first index is not set. It has never seen before. So if it is never seen before, you set the first index as current index, which is I, right? So we have this if condition here, right? This is C++ code, and this side we have Java code. So we have this if condition here. If first index is -1, then we set the first index of current character as current index in the string, right? We use str.caret to get the character at given index in Java, and we can directly use stri in C++. So we get this character and we set its first index as I if it's not present already. If it's present already, it means it's a repeating character, right? And if it's a repeating character, then we see, is it the leftmost repeating character? And how do you see? We keep track of the minimum index that we have seen so far in a variable called result, right? So we initialize our result as infinite, and if we see a smaller value of first index of a character, of a repeating character, then we update our result, which means we are going to store the smallest index of a repeating character, smallest first index of a repeating character. So we begin with A, it was first occurrence, so we set its first occurrence as 0. Now we come to B, it was first occurrence, so we set the first occurrence of B as 1. C is also first occurrence, so we set the first index as current index 2. Now we see a character C, right? And its first index is not -1, its first index is set as 2. It means it's a repeating character. Now we see, is it the leftmost? So what is our current result? Our current result is infinite. So we update the result as first occurrence of this character, and first occurrence of this character was at index 2. Right now the occurrence is at index 3. So we update the result as 2. And how did we get this 2? From this array, we use this index character as an index and got the value. So we update the result as 2. Now we come to I equal to 4. And this character's first index entry is also not -1. So the entry for this character is 1, which is smaller than current result. So we update the result as 1. Now we come to index 5, and this is never seen before. D is never seen before. So we update the index of D first occurrence as current index 5. So this is the status of first index array after all the traversal of the string, and our result remains 1. Now consider a situation when all the characters are distinct. In that case, your result will never be updated and it will remain int max in C++ and integer.max value in Java. This is how we represent infinites in both the languages. So if it remains int max or integer.max value, that means all the characters are distinct. We return -1 in this case. Otherwise, we have the index of leftmost repeating character, we return that index. Now, talking about the time complexity of the solution, this is simply a linear time solution because we are traversing through the string. Talking about the auxiliary space, it requires big O of char as auxiliary space, and char is a constant, 256. So we can say that it's actually time complexity is also length of the string plus alphabet size, because we are initializing this as first index array of char as -1. So we can say time complexity is big O of n, where n is the length of the string, and char is the alphabet size. And auxiliary space is big O of char. So this much auxiliary space. And if you consider char as a constant because it's only 256, you can say time complexity is linear and auxiliary space is big O of 1. So this is one solution. Now please pause this video and think of another solution. The hint for another solution is we can traverse these strings from the right side and we can slightly optimize the solution further. Let us now see next efficient method. In this method, we are going to traverse the string from right to left. Let's understand the method with this example. Let's say we have this string. We create a visited array this time. So we don't need an integer array, we need a boolean array. So we save some space as well if you compare to the previous method. Now what we do is we traverse the string from right side. If we see this character already marked as visited, then we update the result. If it's not already marked as visited, then we mark it as visited. That's the simple idea. That's all we do. So D not visited, we mark it as visited. B not visited, we mark it as visited. C not visited, we mark it as visited. This C visited. Right, so we update the result from -1 to 2, right, index of the C. Now B visited, so we update the result as 1. A not visited, so we mark it as visited. Our final result is 1. Since we are traversing from right to left, the character which is leftmost and repeated will be traversed latest, right? Which will be the latest traverse character, latest traverse repeated character, right? So that's how we don't need to compare previous result with our current value, and we also don't need to store values -1 or first indexes. We can just check whether something is visited or not. Here are C++ and Java implementations. In C++ implementation, I've created a character array, a boolean array of size 256, and I've initialized it with false using the fill function. Fill is part of STL algorithm, right? And then I'm traversing the string from right side. I've simply initialized the result as -1, and if it is visited, then I update the result. If it's not visited, then I mark it as visited. Same thing in Java. In Java, we have a boolean array, and in Java, the good thing is it's by default initialized as false, so we don't need to write anything like fill. Result is initialized as -1. We traverse from the rightmost character. If it's already visited, we update the result. If it's not visited, then we mark it as visited. At the end, we simply return the result. You can notice that here we are doing relatively less number of comparisons, and we are needing a boolean array only. And this solution is also linear, and auxiliary space requirement and time complexity wise, it's same as the previous method. Let us talk about this problem. We are given a string which might contain some repeated characters and some non-repeating characters. Our task is to find out index of the leftmost non-repeating character. Let's understand the problem with these examples. Let's say we have the string GeeksforGeeks. G repeats here, E repeats here, K repeats here, S repeats here. F is the first character that does not repeat. It does not appear again in the string. And what is the index of F? 0, 1, 2, 3, 4, 5. So our output is 5. Now let's see this example. A repeats, B repeats, C repeats. All the characters are repeating here. So there is no non-repeating character. We return -1. Let's see this example, apple. So there are 3 non-repeating characters, A, L and E. We need to return the index of leftmost. So we return the index of 0. Now please pause this video and think of an approach to find index of the leftmost non-repeating character. Let us first talk about a naive solution to solve the problem. The idea is simple. We begin from the first character. We compare with all the other characters, and if it matches with any of the other characters, we set a flag equal to true, which means it's a repeating character. And if it never matches, if flag remains false, then we return that character's index. Because we are traversing from the left to right, the first character that we find which is non-repeating is our answer. So we have 2 loops. For I equal to 0, I is more than start length. We set a flag equal to false, that it's non-repeating initially. And then we compare with all the other characters. When comparing with other characters, we check that the other character should not be same as the current character. Indexes should not be same and characters should be same. In that case, we set the flag as true, that's repeating, right? So if flag never sets to true, it means we did not find any match for this character. So if flag remains false, we return index of this character. We do this for every character from here to here, right? And if we come out, it means we never found a non-repeating character. So we return -1. Talking about the time complexity of the solution, it's clearly big O of n square. We are running 2 loops and it takes big O of 1 auxiliary space. Now please pause this video and think of an approach that is linear time. First, we are going to talk about a linear time approach which requires 2 traversals of the string, and then we are going to talk about an approach which requires only 1 traversal of input string. Let us now talk about a better solution. This is a linear time solution, and the idea is again super simple. We create a count array, the technique that we use in many string problems, that we use characters as an index in the count array, because we know that size of those characters is 256, right? So we create an array of size 256, we initialize this count array as 0, then we traverse through all the characters and we update their counts. So if you see a character, you increment its count, right? Use the character as an index. So if you see this string as an example, you have A, B, B, C, D, A, and initially your count array is 0, and after your first traversal, you have count of A as 2, count of B as 2, count of C as 1, and count of D as 1. Now what all you need to do is, you need to traverse the string again because you want to find the first non-repeating character. So you will have to traverse the string again, and this time you just find the first character whose count is 1, right? So you traverse the string again, right? And you use every character as an index in this count array, and as soon as you find a character whose count is 1, you return index of that character. So you traverse again, this time you see A, its count is 2, you come to B, its count is 2, you come to C, its count is 1, right? So you return the index of character C, so your return value is going to be 0, 1, 2, 3, right? You will get 3. Now what is the time complexity of the solution? It's big O of n time, assuming that alphabet size is constant, and auxiliary space also I can say it's constant, assuming that 256 is a constant value. Now this solution requires 2 traversals of the input string, and interviewers sometimes ask this question this way: how will you do it in 1 traversal of the string? So please pause this video now and try to solve this problem using 1 traversal. Let us now talk about 1 traversal solution to find the first non-repeating character. In this solution, we are traversing the string only once. Then we have one more traversal, but that's a constant loop. If your character size is all ASCII values, then it's only going to run 256 times. And consider large strings, say millions of characters of a string. If we consider those lengths, then this 256 loop is constant and negligible, right? So this actually does 1 traversal of a string and 1 constant loop, right? So it's a constant loop, runs only 256 times. Now, how does the solution work? What we do is we create an array, we call it FI array, which stores first indexes. And finally, it's going to store indexes of only non-repeating characters. For other characters which have repeated, it's going to store -2, and the characters which were never seen, it's going to have -1. So we initialize this FI array as -1 because we initially have not seen any character. Initial value of FI array is all -1. We have initialized it as fill -1, and here we have used arrays.fill as -1. Now we traverse through the string from this character. And when you traverse through a string and you see a character's corresponding value in FI as -1, you see that it's a first instance of this character. So for now it's a non-repeating character. So you store its index. For A, you store its index 0. Now you see a B, it's again the first non-repeating character. So you store its index 1. Now you see a next B. And when you see a next B, it's a repetition, right? So what do? You again mark it -1 or you mark it something else. We can't mark it as -1. Why can't we mark it as -1? See, here are 3 B's. Now if you mark it as -1 here, and when you see a next B, what will happen? You will consider this as a first instance of this character and you will store its index. But we don't want that, right? It's not a first instance, it's not a non-repeating character, it has repeated 3rd time. For that purpose, we introduce a new state, -2. -2 means this character appeared and repeated. So we store -2 in those cases. So if the character is appearing first time, then you store I, its index. If it is repeated, then you store -2. So we update -2 for B. When we come to C, it's the first instance of C. So we mark it its index as 3. When you come to B, we see its value as -2. So we go to the else part. So we rewrite -2 again, right? Now we come to D, it's the first instance, so we store its index 5. A, it's the first instance, so it's not first instance, it has repeated, right? It was 0 earlier, so we mark it as -2. Once we have traversed through the whole string, what are the entries which have non-negative value? B became -1, C is an entry which is non-repeating, right? B became -2, A also became -2 by the end. And D is also an entry that remained positive. So the entries which have non-negative value, 0 can also be a valid value. Suppose there is a character X here. So X is the 0th index non-repeating character. So whatever values are non-negative, they are our non-repeating characters. We just need to find the minimum of those values. For that purpose, we traverse this first index array again. So these values have been updated in the first index. This is only initial value. And we find the minimum value. That's all we do in this loop. And we return this minimum value, which is our answer. So this is how we get the first non-repeating character in 1 traversal. Please note that this solution is 1 traversal for string, and it has one more advantage. Say you have a stream of characters coming. you have a stream of characters coming, say millions of characters keep coming or millions of something keeps coming. Now you want to find non-repeating at any instance, right, at the runtime. So in the count solution that we discussed earlier, you need to know the full string. You can't use that solution for a stream, but this solution can be used for a stream. So this is how we find the first non-repeating character using one traversal of a string. Now let's talk about the time complexity and auxiliary space. Time complexity is clearly big O of n, right, because we have traversed the string once. Or you can say theta of n because we always traverse the string once, right? It's not that we stop in the middle, right? So it's theta n, considering that character size is constant, alphabet size is constant, and auxiliary space can also be considered constant, assuming that alphabet size is constant. And if we want to be more precise when we're talking about time complexity, we can say it takes theta of n plus char time, this much time it takes, and it takes theta of char space, this much extra space it takes, right? So this is one traversal and this time complexity and auxiliary space solution. Let us talk about this problem. We are given a string which may contain multiple words separated by space. Our task is to reverse the order of words in the given string. For example, if our input string is welcome to GFG, then GFG is the last word. In our output, it should be the first word. 2 is the second last word, it should be the second word. Welcome is the first word, it should be the last word in the output string. In this string, coding should come first, love should come second, and I should come first. In this string, there is only one word, ABC, so there is no change in this string. Now please pause this video and try to write down a function that takes a string as a character array as an argument and reverses word in the given string. You need to reverse the words in place. You need to modify the same character array in place of using any auxiliary space. Let us first talk about a naive solution to solve the problem. The naive solution is to create a stack, traverse the given string one by one from the first character. You stop when you see a space, right? When you see a space, it means you have seen a word. So what you do is you take all these characters, put them into a string and put this string into the stack. Push the string into the stack, right? So you are going to push welcome first. And after a space, you begin the new word. Then again you see a space, you know that 2 is a word. So you push 2 into the stack. Then you see GFG is a new word. You push GFG into the stack. So this way you get welcome to GFG in this stack, this form. Now what all you need to do is you need to take out these individual words from the stack and append them to an empty string, and that string becomes your answer. So I again make my string empty, then I take out the first word and I make str equal to GFG. Then I take out 2 and I make it GFG2. Then I take out welcome and append welcome to it. So when I take out a word, before appending the word, I also append a space. So this is how I get the reverse words in the given string using a stack. This solution requires auxiliary space. How much auxiliary space it requires? It first of all requires auxiliary space equal to the number of words, right? Those many entries are required in the stack. Also, it requires auxiliary space for the individual words. And how many characters we have together in all individual words? It's going to be big O of n, where n is the length of the given string. So it requires big O of n auxiliary space. How can we do it in place? How can we do it without using auxiliary space? Now please pause this video and try to think of a solution that works with big O of 1 auxiliary space. Let us now talk about an efficient solution that requires constant auxiliary space. It mainly reverses the words within the character array only. Let's get the idea with this example. So the idea is this: we first reverse the individual words and then we reverse the whole string. That's really interesting solution for this problem. Let's say we have our input string as A, B, C, B, C, D, E, F. This is our input string. Now what we do is we traverse through the string, and whenever we see a space, we know that it's end of a word. So what we do is we maintain begin of a word and end of a word, and between those two things we reverse the individual words. So we reverse the first word, we get CBA. We reverse the second word, we get DCB. We reverse the third word, we get FE. Now, once we reverse the individual words and we modify the string to this or character array to this, our task is to simply reverse the whole array or reverse the whole string, and we get the output. Now, if I reverse this whole thing, I'll get E, F, then B, then space, then B, then C, then D, B, C, D, then space, then A, then B, then C. So the idea is this: traverse through the given character array, reverse the individual words, then reverse the whole string or whole array. That's the simple idea. Let's now see how does this implementation work. So here is implementation which is written close to both C++ and Java. This is the main function. This is a supporting function. This function only reverses the characters from low index to high index in a character array. In C++, you have a direct function for this purpose. You can call reverse function by passing iterators. For example, I can pass here, instead of calling this, making my own reverse function and calling this function here, I can pass str plus start as first iterator, and I can pass str plus end as this other iterator, and it will reverse the string. Here I've written code which is close to both C++ and Java. So in this code, I am passing character array as an argument, size as another argument. You can skip passing size in Java. You can get the size as str.length inside the function itself. And the swap function is not available in Java, so you can write the simple swap function temp equal to str low, and then str low equal to str high, then str high equal to temp. Right, so this is about syntaxes into both the languages. Now let's see the implementation logic. So what are we doing here? We are traversing through all the characters one by one, right? We have initialized the starting point of the current word as 0. Now we are finding the ending point of the current word so that we can reverse between start and end. So we ignore all the characters which are not spaces. And as soon as we find a space, we know that the characters from previous start to end -1 are forming a word, right? So we simply reverse the word, and we set the starting point for the next word as end +1, and then we keep on doing it. So when we go to the next end, if it's not a space, we keep on incrementing end, and when we find a space, we know that characters from start to end -1 are forming a word. We again reverse them. So this is how we keep on reversing all the words. The one thing to note here is it would not reverse the last word, because you are reversing a word when you are seeing a space after it. But there would not be any space after the last word. So we are explicitly reversing the last word. We reverse the last word. We know that last word would exist from start to end -1, right? The start that we set up here, which is after the previous word, right? After the previous word that we reversed, from that point to end -1, we have the last word. Now we reverse the last word, and after reversing the last word, this is simple code for reversing the whole string. Here is a dry run of this code. Say our string is welcome to GFG. Here G is capital and this G is small. I have intentionally done it so that reverse we can see when it is reversed, right? Now start is 0. N is 14, which is the length of the string, right? 0 to 13 are the indexes, and we have the length of the string as 14. Now we set start equal to 0 and we run this loop. We run this loop from 0 to n -1, which means 13. When we run for 0, we see a character which is W. It's not a space, so we ignore it. We ignore this space, this character also. This is not a space. This is also not a space. This is also not a space. When we come to this space, right? When we come to index 7, this is when we go inside this if condition, right? So we don't do anything for 0, 1, 2, 3, 4, 5, 6. When we see a 7, we go inside this if condition when our end is 7. And what do we do inside this if condition? We reverse the characters from start to end -1, which means 0 to 6. So these are the characters which are reversed, and these are the reversed characters, right? So we get the string as EMOCLEW, EMOCLEW. After reversing these, we set the start equal to end plus 1. So our start now becomes 8, which is beginning of the next word. I am assuming that all the words are separated by a single space. In case you want to handle multiple spaces, you can easily extend this code. You can, instead of if condition, you can write a while loop. While when you see a space, you run a while loop inside it. I am assuming here that all the words are separated by a single space. So in this code, I am not handling the cases when you have multiple spaces between the word. In case you want to extend this code to handle multiple spaces, you can write a while loop inside it, right? And this while loop keeps on running while there are spaces, right? So after start is set to 8, we again run this loop, right? Now we see a T, we ignore it. We see an O, we ignore it. So we don't make any change for 8 and 9. When we come to 10, we see a space. Now when we see a space, we reverse the word from start to end minus 1. So we reverse this TO, right? So it becomes OT. Now we again do not make any change for these indexes 11, 12, 13. And after 13, our loop stops because we have reached the end of the string or character array. After we have come out of the loop, what we do is we reverse the last word because the last word is not reversed yet. Although we have appropriate starting point of this word is 11, but we have not reversed it because there was no space after it. So what we do is we reverse the last word by simply calling this start to n minus 1, right? We know the start and we know that last word must be till n minus 1. Here I am again assuming that there are no trailing spaces. You can make modifications to this code to handle the trailing spaces as well. So we reverse the last word by making a call to start to n minus 1, and after reversing the last word, our string becomes this, right? So we have reversed all individual words at this point after we are finished with the loop and finished with the statement. So this is first phase of our code. We have reversed individual words. Now this is the last phase or the second phase where we reverse the whole string from 0 to n minus 1. After reversing the whole string, we get G, F, G, then space, then T, O, then W, E, L, C, O, M, E. So we get the words reversed. Our original string was welcome to GFG. Our modified string is GFG to welcome. So we have reversed all the words without using an auxiliary array or an auxiliary space of non-constant size. We're just using some constant variables. Let us now talk about some language specific things. If user gives you a Java string as input and wants you to reverse individual words, you can use toChar array to convert the string into a character array, and then you can use this function. And if you wish to get back a string again, you can create a string in Java using character array as a constructor. In the constructor parameter of a string, you can pass this str as this, and you can return this string, newly created string after these modifications, right? So this is how you can handle strings in Java, and this is better than using the string object because strings are immutable. And if you use a string and implement this logic, that would be complex. It would be complex even if you use mutable things like a string builder or string buffer. This character array logic implementation in Java is super easy compared to using built-in classes. So if you are given a string as input, you can use these syntaxes to convert a string into a character array. You can use this line particularly, right? And to convert the character array back to a string, you can use this line. Right, so this will be not big of one extra space, it will be requiring extra space because you are copying a string to an auxiliary array and then copying auxiliary back to a new string, but it's still better than using a string object. Now talking about C++ implementation, if you initialize your string or your character array this way using double quotes, then be careful when you are using this function. And if you are using size of operator to get the size of this character array, for example, size of str divided by size of str0. If you are using that syntax to know the size of this character array, then you will have one extra size, because when you initialize a double quoted string and assign it to a character array, C++ compiler by default adds an extra character \0, right? Even if you are not writing it, there will be a \0 at the end of the string. And size of the string will not be 14, it will be 15, right? These many characters total count to 14, we just saw, right? And your compiler will add a \0 and will make the size 15. And if you pass that size as it is, then your whole logic will not work, right? Because your size is not correct, right? So here also you will see problem, here also you will see problems, and here also you will see problems. So to fix this, what you can do is you can pass n-1 as a parameter if you are initializing your input string using double quotes. So this is all about some syntax specific issues, but this implementation is really great. If you have a character array as input, you can reverse individual words without using auxiliary space. Let us talk about this popular problem called pattern searching problem. We are given a text, a big string, and a pattern, a small string. Our task is to find all occurrences of this pattern in the text. If pattern is not present, then we need to print not present. So in this example, we have a big string GeeksforGeeks, it's our text string, and a small pattern string EKS. EKS is present in the text at index 2 and at index 10, right? Indexes begin from 0. So this is 2 and this is index 10. So our output is 2 and 10. Let's see this example now. These are two corner cases. In this corner case, your pattern is present everywhere. Your pattern is present at index 0, index 1 and index 2, right? Maximum possible occurrences. So our output is 0, 1, 2. And this is an example where pattern is not present at all. ABD is not present as a substring anywhere in this text, right? So our output is not present. So this is the pattern searching problem. There exists many algorithms to solve the problem because this is such a common occurring problem in computer science. You work on a file, whether it is a programming file or MS Word file, you always search for a string, right? That's a pattern searching problem. Google search is also kind of pattern searching problem. DNA matching, that also is kind of pattern searching problem. Regular expression searches, which are also variations of pattern searching problems. So pattern searching is a very frequent problem in computer science. So there are many algorithms. We are going to do an overview of some of those algorithms for this simple pattern searching problem. Here is overview of the pattern searching algorithm. Since pattern searching is such a popular problem, there exist many algorithms to solve the problem. I have written here the most popular algorithms. So here are the algorithms and there are time complexities. In the time complexity computations, M is the pattern length and N is the text length. N is bigger than or equal to M, right? So the first algorithm is naive pattern searching algorithm. It's a simple algorithm. Take the pattern, compare it with every window of the text one by one, and if it matches, then print it. So the time complexity of this algorithm is n minus m plus 1 into m. We are going to discuss this algorithm in detail in a separate video. The next algorithm is naive algorithm when pattern characters are distinct. If your pattern contains all distinct characters, then you can improve the naive algorithm to work in big O of n time. The naive algorithm performs poor only when there are repetitions in the pattern and text. Next algorithm is RABIN-KARP algorithm. RABIN-KARP algorithm uses the idea of rolling hash to optimize the naive algorithm. The idea is this: instead of going one by one and matching all the characters every time, you first compute a hash function, and if hash function is matching, then only match the individual characters. So the RABIN-KARP algorithm works better than the naive algorithm in general because it doesn't always match all the characters, it first matches the hash function. But in worst case, what might happen is hash function matches every time. So it might perform poorer than the naive algorithm. And an upper bound on the time complexity of RABIN-KARP is n minus m plus 1 into m. Same as naive algorithm. Next algorithm is KMP algorithm, and this is really one of the most popular and complicated algorithms in computer science. This algorithm takes big O of n time, linear time algorithm for any pattern or any kind of text. Right? If you have a pattern in a text, it will give you the occurrences of the pattern in the text in linear time. The thing about these two algorithms is they pre-process the pattern. It pre-computes the hash function, and this KMP algorithm pre-process the redundancies within the pattern. So the idea of KMP algorithm is for distinct characters, your naive is good. How to handle the redundancies. So KMP pre-processes those redundancies by pre-computing an LPS array of size equal to the pattern length, right? So it pre-processes the pattern, builds an LPS array, and then using this LPS array, it finds the occurrences of pattern in the text. Here LPS is longest proper prefix, which is also suffix. We are going to talk about KMP and RABIN KARP algorithms in detail in separate videos. So KMP is not the only algorithm which is linear. There are many other popular algorithms as well, but KMP is the most popular. The other algorithms are Boyer-Moore algorithm, Z algorithm. These two algorithms are also linear in time. In fact, Z algorithm is really simple compared to KMP algorithm. The last thing is suffix tree. It's not an algorithm, it's a data structure. And the idea of suffix tree is pre-process the text. So if you have a fixed text, for example, a Gita book or a pre-processed web page, and this web page is not going to change, then you can search a pattern in this fixed text by pre-processing the text. So you pre-process the text and take some time to pre-process the text, and this time is going to be at least linear in terms of the text length. So you take that much time, and then if you have thousands of searches or millions of searches on this text for different patterns, you can perform those searches in big O of m time, where m is the length of the pattern. Here n is the length of the text, right, big text, and here m is the length of the pattern, the small pattern that you are searching repeatedly. But the difference here is you are pre-processing the pattern here. Here you are pre-processing the big text so that multiple small searches can be performed efficiently. We are not going to discuss suffix tree in detail, but we are going to discuss trie data structure, and suffix tree is mainly built using the idea of trie. We consider all the suffixes and make a trie kind of data structure for these suffixes. But the great thing about suffix tree is it works in linear time in terms of pattern length. So if you have a text which does not change regularly, which is a fixed text, you can use suffix tree to quickly do the searches. But if you have a text that keeps on changing, for example, your MS Word document or your programs which keeps on changing, which are not fixed, in those cases we need to use one of those algorithms. So this is an overview of algorithms. We are going to talk about these 4 topics in upcoming different videos. Hi, in this video we are going to talk about naive pattern searching algorithm. Before we talk about the algorithm, let's first see the problem. The problem is we are given a text and a pattern. We need to find all indexes where this pattern occurs in the text. So if your text is AB, 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 CD and your pattern is AB, AB, you can notice that this pattern appears at index 0, right? It's present here, AB, AB. It also appears at index 2, AB, AB, right? And at other indexes 3, 4, 5, 6, 7, it does not appear. So our output is 0 and 2. In this example, our pattern is ABCD and our text is ABC, ABCD. Now it does not appear at 0 because 3 characters match, but the 4th character does not match, right? ABC are matching, but A and D do not match. So it does not appear at 0, it appears at index 3, right? So we write output as 3. It matches here completely. A matches with A, B matches with B, C matches with D, C and D matches with D. This is an interesting pattern. You have all A's in the text, you have all A's in the pattern. So in these cases, your pattern appears at all valid indexes. It appears at index 0, appears at index 1, appears at index 2. After that, it's not possible because only 3 characters left. So output is 0, 1, 2. It appears at all indexes 0 to 2. And if your pattern does not appear in the text, then you don't need to print anything. Now please pause this video and try to write down a function that takes a pattern as an argument, a text as an argument, and this function prints all the indexes where this pattern appears in the text. Let us now talk about naive pattern searching algorithm to solve the problem. The idea of naive pattern searching algorithm is really simple. We have a text and we have a pattern. We need to find all indexes where this pattern is present. So what we do is we slide this pattern over the text one by one. We first compare these 4 characters with these 4 characters, and then we slide it and compare these 4 characters with the pattern. Then we compare these 4 characters with the pattern, and then we compare these 4 characters with the pattern. Now how does this sliding happen? We are running an index I equal to 0, I smaller than equal to n minus m. How do we get this number n minus m? See, the indexes here are 0, 1, 2, 3, 4, 5, 6. And here are 0, 1, 2, 3. What is n? Number of characters in the text. How many characters we have in the text? 7. How many characters in the pattern? 4. Now, how long we will slide it? We will try it at index 0 with these 4 characters, then at 1, then at 2, then at 3. And what is the last index that we try? 7 minus 4. So 7 minus 4 is the last point till we run this loop, and I is the starting point of the current window in the text. So when we are at window starting with index I, we compare characters of the pattern and text one by one. And if all characters match, we print that particular index. So here is C++ implementation, and this side we have Java implementation. You can notice in both the implementations, we are running a loop for I equal to 0, I smaller than equal to n minus m, which is a starting point of the current window. Then to match individual characters, we run a loop for j equal to 0, j smaller than m, j plus plus, which means we are matching all the characters of the pattern with all the characters of the current window of the text. And at any point, if we find a mismatch, we break the loop. And if all characters match, if j becomes m while you are matching the characters, then you print that particular index of the text that we found the pattern at this index. Now let's understand this code with this example. We have I equal to 0, j begins from here. Now j equal to 0, j smaller than m, match all the characters. So j equal to 0 matching, j equal to 1 matching, j equal to 2 matching, j equal to 3 not matching. So we break the loop. And when we broke the loop, j was not equal to m. What is m? M is 4. J was 3, right? So what we do now, we begin the next iteration of the outer loop. When you begin the next iteration of the outer loop, you begin with I equal to 1. So what are you going to do now? You are going to slide the pattern here. You're going to begin comparing the current window of text with pattern at index 1. So A and B, they are compared, they do not match. So you come out of the loop for j equal to 0 itself. Since j is not m, you don't print that index, right? So you now come here, A, B, C, D. Again you come out at index 0 itself because these two are not matching. Then you move the window to next character, your next iteration of the loop for I equal to 3, and this is the last iteration. Here you again match the characters, j equal to 0 matching, j equal to 1 matching, j equal to 2 matching, j equal to 3 matching. So all the characters are matching. You come out of the loop because j became m. So when you come out of the loop and if j is m, then you print that index. So you print the output as 3. Pattern found at index 3. That's the simple idea. Take the pattern, slide it over the text one by one and compare the characters, and at any point if you don't find a match, then current window cannot match, right? And you can notice the indexes j is 0 to m minus 1 every time we start matching from the beginning of the pattern. And in the text we are using the indexes I plus j because I is the starting point of the current window and j is the shift from the starting point. So this is how this naive algorithm works. Now talking about the time complexity of this naive algorithm, if you take a look at this algorithm, we have a loop that runs n minus m plus 1 times, right? 0 to n minus m. So it runs n minus m plus 1 times in the worst case, and multiplied by, actually there is no worst case, it's always going to run it n minus m plus 1 times. So it's always n minus m plus 1 times this outer loop is going to run. This inner loop is, worst case will run m times for every shift, and you will have m times for every shift in the worst case. So an upper bound on the time complexity is n minus m plus 1 into big O of m. into m. And when will the worst case happen? Imagine this is string, the last example that we talked about. When you have all A's in the text and you have 3 A's in the pattern. What will happen here? When you start from this window, they 3 will match. So this loop will run all 3 times. Then you will shift it here. Again, all 3 characters will match. Right? So this will run m times. Again, all characters will match. So it's going to run exactly m times for these kind of examples. Right? So in the worst case, this is the time taken by this algorithm. So I've used big O. It's an upper bound. It might take less than this because it doesn't have to run m times every time. Now talking about auxiliary space, it takes big O of 1 auxiliary space. Please note that naive pattern searching algorithm is not the best way to do pattern searching. It's quadratic time algorithm, and there exists linear time algorithms which can search a pattern in a text. And these algorithms are KMP algorithm, Z algorithm. Even RABIN KARP is better than naive, although RABIN KARP is also quadratic in the worst case. We'll talk about these algorithms in the upcoming videos. Let us talk about this problem. We are given a text and a pattern. We need to print all occurrences of the pattern present in the text. Here we are also given that the pattern has all distinct characters, right? Pattern has all distinct characters. Let's understand the problem with these examples. Let's say we have the pattern as this and text is this and pattern is this. So pattern appears at index 3 here, 0, 1, 2, 3, and also appears at index 7, 4, 5, 6, 7. So our output is 3 and 7. Let's see this example. Text is this and pattern is this. Pattern appears at index 2 and also appears at index 10, right? Let's see this example. Pattern does not appear in the text at all. So our output is empty. We don't print anything. Now please pause this video and think of a solution to solve the problem. We have already talked about a naive solution to solve the problem. And we can apply the naive solution here. The time complexity of the naive solution was big O of n minus m plus 1 into m. Naive solution works for all kind of patterns, whether they have repeated characters or distinct characters. Now the question is, can you optimize the naive solution to work in linear time for this particular case when you have distinct characters in the pattern? Now please pause this video, take a look at the naive algorithm and try to modify it so that it works in linear time when you are given that all the pattern characters are distinct. Let us take a look at this improved naive searching algorithm for the cases when pattern has distinct characters. This works in linear time. Here I have written a pseudocode. This code is close to both C++ and Java. If you are programming in Java, then you will write a string before this text, right, where S is in capital letter, string before this pattern. And if you're programming in C++, then you will write string in small letters. And in C++, you will pass it as a reference also using ampersand sign for the optimization purpose. And if you see rest of the code, this is also same in C++ and Java. This is also same. Here is a slight difference. This is more C++ style code. In Java, we will write pat.caret ctext.caret, right? We get the indexes at characters at the given index using char at in Java, right? So this is how this is what we'll insert, right? So this is how we get the character at a given index. This is print statement here. If you're programming in C++, then you will write cout here. If you're programming in Java, then you will write system.out.print. Rest of the syntax is same in both C++ and Java. Okay, let's now get an idea how does this algorithm work. We can get an idea with an example first, right, before we take a look at the algorithm. So what happens in this algorithm? We optimize under the assumption that pattern has distinct characters. How do we optimize? This algorithm works like naive. We slide the pattern over the text one by one. You can notice that we have a loop here. I equal to 0, I is more than equal to n minus m. But there is no I plus plus here. I plus plus is missing here. Right? We are doing I plus plus or we are doing I equal to I plus j. Let's see how does this work. So we slide the pattern over the text one by one, and we, like the naive algorithm, we have an inner loop that matches pattern j with text I plus j, right? We match all the characters one by one. So we begin with I equal to 0, we match A with A, B with B, C with C, and A and D. This is where we see a mismatch. Now in the naive algorithm, what we would have done is, we would have slided this pattern by one, and then we would have started A with B, right? We would have done this. We would have moved it here, right, in I equal to 0, and then we would have started from here to here matching. But in this algorithm, we take the advantage of the fact that all the pattern characters are distinct. Since all the characters are distinct, and some characters, here 3 characters, have matched with the pattern text 3 characters, these 3 characters are matched, and these characters are distinct. So can this character A match with this, right? If I slide this pattern, can I conclude that it would never match? Yes, I can conclude that. This A would never match this B, this C. I can safely shift this pattern by 3 positions because 3 characters matched, right? So I can safely move this pattern here directly without matching it 1 and 2, I can simply move it here, A, B, C, D. And how can I do this? What is the logic behind it? The logic is this. See, these characters matched, these characters matched, these characters matched, and these characters are distinct, right? So this character cannot be same as this. This means this character cannot be same as this. So the shift where we move A here below the C, it's not a valid shift. It won't ever lead to an answer. So if same is the logic for B. These 2 characters match and these 2 characters are distinct, they are not same. So if I shift this pattern over this text by 1 and bring this A below B, will it ever match? No, because they are same but they are distinct. So it cannot be same as this. It cannot be same as this, right? It can, same logic, it cannot be same as this because these 3 characters are matched with 3 characters of the pattern. They are distinct. It means they are also distinct. This A is different from this C, this A is different from this B. So I can safely move this A here, and that's the implementation. If you see some mismatch after some matches, you can simply forward or slide the pattern by J. That's what I've done here. If J is 0, then I switch to naive algorithm. If the first character itself did not match, then I move like naive algorithm, I do I++, and if J is not 0, that means I saw a mismatch after some matches, right? So what I do is, I slide the pattern over the text by J because these characters can never match with the first character itself. So I slide the pattern here, now I again match, A matches with A, B matches with B, C matches with C, D matches with D. So I print the output as what is the shift here? It's 0, 1, 2, 3. So I print the output as 3. And that's where I end the algorithm. Let us now see one more example to get an idea. And let's run this algorithm step by step for this example. Here, what is n? N is number of characters in the text. So this is 4 plus 4, 8 plus 4, 12. N is 12 and M is 4. So we've computed n and m. Now we run the loop for I equal to 0, I is smaller than n minus is smaller than equal to n minus m is 8. So we run this till the index 8. We learned till this point. Now inside this loop, we run another loop where we start matching characters. So for I equal to 0, what is going to happen? We are going to match A with A, B with B, C with C, and E with D. E and D do not match. So we break the loop. When we break the loop, we check if J is equal to M, if all the characters matched. All characters did not match. So J is not M. Is J 0? No. So J is a non-zero value not equal to M. It means we have seen a mismatch after certain matches. So what we do is, we slide the pattern over the text by more than 1, right? So what is this value J now? J is 3. So we make I equal to 3, right? Here we make I equal to I plus J, right? And J was 3, 0, 1, 2, 3, right? So I becomes 3 now. Now I becomes 3, it means your pattern has moved here. It's A, B, C, D. Now we again match characters E and A. They do not match, right? So I begin with the next iteration with I equal to 3, and the first character itself did not match. So J is 0. So we come here, and now what we do is we make I equal to 4. We simply increment I by 1. We go like naive algorithm in such cases. Now pattern has moved here, A, B, C, D. This time we again start matching with I and J, pattern J and text I plus J. So A and B match, B and B match, C and D do not match. So we see a mismatch, right? And what is J? J is 2. So I becomes now 3 plus 2, 5. Sorry, 4 plus 2, 6. I becomes now 6. I was 4 and 2 added, so it becomes 6. So now I become 6, it means you will move the pattern here, A, B, C, D. Now you again start matching, and E and A, they do not match. So you see a mismatch at the first character itself. So you go like a naive algorithm. So what you do I plus plus. So you move I here, A, B, C, D. Again the first characters do not match, right? So you will go like naive algorithm and you will come here. So let me write down here. So I equal to 7, we went like a naive algorithm, right? I equal to 6 and 7, we went both at indexes, we went like naive algorithm. Let's now see I equal to 8, what happens. At I equal to 8, we run the loop again, J equal to 0 matching, J equal to 1 matching, 2 matching, 3 matching. So J becomes 4, you come out of the loop and you print this instance. So what is this index? Out, 8. So you get 8 on the screen, right? And you're finished because your I was n minus m in the last iteration and you have printed occurrence of the pattern. Now how is this algorithm linear time? Now this is interesting because there are two nested loops and I'm claiming that it's a linear time algorithm, and I think if you take a closer look you can guess it yourself. What is happening here? We are running a loop inside another loop, and inside this loop we do some iterations. So if I do some iterations, say I do 4 iterations inside, then I save 4 iterations of the outside loop. If you look at this, if you're running J equal to more than 0 times, then you are shifting the I that much by that much value. So overall you are linear. If you did 4 iterations, inner iterations, then you jumped by 4 in the outer iteration. So overall time complexity of this whole implementation is linear. It runs theta n time, right? It takes theta n time to find out all the occurrences of the pattern in the text. Hi, in this video we are going to talk about RABIN KARP string searching algorithm. Let's understand the problem first. We have this text and a pattern. We need to find all occurrences of this pattern in the given text. These are the indexes of the characters in the text. So character A is at index 0, this is at 1, this is 2, and so on. Now we see this pattern, we can notice that this is present at index 3, right? At index 3 it begins and it has all the occurrences of the characters of the pattern in the same order. Then it also occurs at index 7. So our output is 3 and 7 separated by a space. Now let's see this text and this pattern. This pattern appears at index 0, then at index 1, then at index 2. So our output is 0, 1, 2. Let's now see this. We have this text A, B, C, D and our pattern is X, Y, Z. So pattern is not present in the text, so our output is not found. We have already talked about naive string searching algorithm, which is quadratic in time. Now we are going to talk about an optimized algorithm. This algorithm is also quadratic in worst case, but it works better in general. Like naive algorithm, in RABIN KARP also, we slide the pattern over the text one by one. But unlike naive algorithm, when we slide the pattern, we do not start comparing the individual characters immediately. What we do is, we use the idea of hashing. We compute a hash value of the pattern, which is an integer value, and hash value of every window of the text. If these two hash values, these two integer values match, then only we compare individual characters. That way, we save lots of comparisons for bigger patterns, especially for the bigger patterns. Let us now get an idea of working of RABIN KARP algorithm. Let's consider this text and this pattern. These are the indexes of characters in this text. We are going to slide this pattern over this text one by one, starting from index 0 to index 7. This is like naive algorithm, right? But unlike naive algorithm, when we are at current window of text, we do not compare all characters one by one. Rather, what we do is we compare hash value of pattern with current hash value of text. If these two hash values match, then only we compare the individual characters. And if individual characters also match, then we print that particular index value. And then we move to the next window. We are going to use this term P for hash value of pattern and this term T for hash value of current window of text. Let us first understand RABIN KARP with a very simple hash function, although it's not a good hash function. We will see the problem with this hash functions later. So the hash function that we are going to use is simply sum the values of individual characters. Also, for simplification, we are not considering ASCII values. We are considering these values. We are considering 1 for A, 2 for B, 3 for C, and so on. And we are considering only 5 possible characters in pattern and text for simplicity of understanding. So what we do is, we first compute the hash value of pattern, and this hash value is 1 plus 2 plus 3, which is 6, right? 1 for A, 2 for B, and 3 for C. Now we slide this pattern over the text one by one, and we begin with this index I equal to 0. And at this index, we compute the hash value of current window of text, T. And what is this value? 1 plus 2 plus 4. We have 4 for T, right? And this value is 7. So we first compare these two integer values, 6 and 7. They do not match. So we simply skip this particular window of text. Now we move to the next window, and again we compare the hash values. What is the hash value of next window? It's 2 plus 4 plus 1, 7. And this value is 6. 7 and 6 do not match. So we skip the next window also. Now we come to the next window. And what is the hash value of current window? It is 4 plus 1 plus 2. Right? Again 7 do not match. Then we come to I equal to 3. At I equal to 3, we have the hash value as 6. And what is hash value of pattern? That is also 6. So they match. Now we are going to match individual characters. We are going to match this A with A, then this B with B, then the C with the C. And since all the characters match, they are in same order, we print the output as 3, that we found the pattern at index 3. Now we move to the next window, I equal to 4. And for this window, we have the hash value as 2 plus 3 plus 2, which is again 7. So they do not match. Hash values do not match. We simply do not match the individual characters. Now we come to I equal to 5. And this is interesting. What is the hash value now? Hash value for I equal to 5 is 3 plus 2 plus 1, 6. Right? 3 plus 2 plus 1, 6. And hash value of our pattern is also 6. So what are we going to do now? We are going to match individual characters one by one. And these individual characters are not going to match. For example, you will match C with A, and at this point only you will realize that this is not a valid match. And this particular hash value match is called spurious hit. We matched the hash values, but characters were not matching, right? Now we go to the next window, and we again compare the hash values first. Hash value is 5 here, and our pattern hash value is 6, so they do not match, so we simply skip it. Now we come to 7, and hash values match. Now we match individual characters, A and A match, B and B match, C and C match. So we print this particular index 7 also as an output. So we get 3 and 7 as output. Now a simple question arises in our mind. We are doing sum of values in the hash function. This is again big O of m work if m is the length of the pattern, because every window is going to be of size m, and for every window you are going to sum the ASCII values, and it's again looking like naive. But if you take a look at this, you can optimize this hash value computation. You can compute the hash value of current window by subtracting the ASCII value or value of the last character of previous window and adding the value of the last character of current window. And that's the main idea of RABIN KARP. And this is called rolling hash, where we can compute the next hash using previous hash in constant time. Here is expression for simple rolling hash. Here m is the length of pattern. We can compute hash value for window at index I plus 1 using existing hash value for window at index I by simply adding last character of I plus 1th window and subtracting the last character of ith window. For example, using this hash at index I equal to 3, we can compute the hash for 4. We can simply take this value 6, subtract this value 1 from it, and add this value 2 to it. So we will have 6 minus 1 plus 2, 7. This is how we can compute the rolling hash. For a pattern of length 3, it might not be looking like a big optimization, but imagine patterns of lengths hundreds or thousands. We are simply doing one addition, one subtraction rather than traversing through those hundreds of characters. So this rolling hash can be computed in big O of one time using the previous hash value. We just talked about a simple hash function. This simple hash function causes many spurious hits, especially when the character set is small. Whenever you have a permutation of pattern present in the text, it's going to cause a match in hash values. For example, two words, God and Dog, they are going to have the same hash values because the sum of ASCII values of different permutations of characters are going to be same. To avoid this issue, we have an improved hash function, and in this hash function we introduce a variable d. Instead of doing simply sum of ASCII values, we do a weighted sum where we multiply ASCII values or values with powers of d, right? So here I'm not using ASCII values, I'm using these values corresponding to the characters. So we multiply these values with powers of d. We multiply the first character with d square. So please note that there are 3 characters in the pattern, so I'm considering a window of size 3, and the first character is multiplied by the length of the pattern minus 1, right? So here the length is 3, so we are going to multiply it with d square. Then we multiply with d raised to the power 1, then d raised to the power 0, and that's how we get this hash value for this particular string. Similarly, we get this hash value for this string. D's value is 4. We multiply 4 into d square, then we multiply 1 into d, then 2 into d raised to the power 0, and we get this ASCII value. So now we have a better hash function which is using weighted sum. How do we ensure that this function is also rolling? How do we make sure that we can compute the hash function of next window of text using the existing hash value of the previous window? Fortunately, we have a formula here. We can get this function for window starting with index I plus 1 using the value of window with index starting with I. We subtract the first character of previous window, multiply by d raised to the power m minus 1, and then we add the last character of current window. That's how we get the hash value of the current window. Let's understand this formula with these examples. So we first compute the hash value t0 for the first window explicitly. I just simply use the above formula, above computation to get the hash function for first window. Now to compute the hash function of the next window, I'm using this formula. And how are we using it? We have d equal to 5, t naught equal to 39 minus 1 into 5 square plus 1, right? And that's how we get the value 71. And to compute the hash function of this window starting with 2, t2, we use the value of t1. We do subtract the last character of previous window, 2 into 5 square, and add the last character of current window. So current window begins with 2, its last character is b, So we add 2 here for b and we get this hash function. Now T3, again we use the existing value of T2. We subtract 4 into 5 square, the first character of previous window, right? And multiplied by d raised to the power m minus 1, and we add the last character of current window. This computation is actually similar to what we do in decimal arithmetic. For example, if you consider this text of simple decimal digits and you consider d equal to 10, m equal to 4, the pattern length is 4, and if we simply take the values of the windows, so the value of first window is clearly 1324. Now we need to compute the value of this window using the value of this window. So we want to get the value 3245 using 1324. How do we get this value? We are simply going to take the last 3 digits of this, right? Decimal value corresponding to last 3 digits, going to multiply it with 10, and then we are going to add 5, right? That's what we want, right? We want 3245. Now, how do I write formally so that I can convert this number into this number? For that, what I'll do is, I'll take 1324 and I'll subtract 1 into 10 raised to the power 3 from it, right? Pattern length minus 1. So if you do the subtraction, what will you get? You will get 324. And if you multiply this number with 10, what you will get? You will get 3240. And now what all you need to do is, you need to add 5 to it. Now if you add 5 to it, what will you get? You will get, this number you will get as 324 multiplied by 10 plus 5. So you get your required number, which is value of the next window, 3245. You can consider these computations same as this computation. This is just in base 5. We have 5 characters. We have taken d equal to 5. Here we had total 10 possible digits. So we took d equal to 10 and we took the window size as 4. Here the window size is 3. And we are doing the exactly same in base 5 for these characters as digits, right? What we did here to find the value of this window using the value of this window. Let us now talk about implementation of RABIN KARP algorithm. The code written here is a pseudocode for RABIN KARP. This code is very close to C++ and Java codes. If you take a closer look at this code, you can notice that at many places we are doing computations under modulo Q, right? This is under modulo Q, this is under modulo Q, this is under modulo Q, and this computation is also under modulo Q. The reason for doing this modulo computation is when we are doing weighted sum of ASCII values of characters of a string, this number can become really large even for smaller strings. So we compute this number under modulo so that we can store it in an integer variable or a long int variable. This q that we have written here is generally a prime number, and we would like to choose q as big as possible so that there are less spurious hits. Because if your prime number is small and if you're doing modulo under this prime number, you are going to have very few values as a result of modulo. For example, if q is 13, then the result numbers are going to be from 0 to 12, which is a very small number. And as per Pigeonhole principle, many spurious hits are possible. Okay, so we have computations under modulo. Let's now talk about this code step by step. The first thing that we do is we pre-compute this value, d raised to the power m minus 1 modulo q. We are going to use this value in this computation. So instead of doing this computation again and again inside a loop, we have pre-computed this value. Now we are going to compute hash function for first window of text and hash function for the pattern. And to do these hash function computations, we are going to follow Horner's rule. Let's understand this Horner's rule. So if you want to compute the hash function of the pattern, basically we want to compute this value. We want to take the ASCII value pattern 0. We want to multiply it with d raised to the power m minus 1. Then we want to add it with pattern 1 with d raised to the multiplication d raised to the power m minus 2 and so on. Now one simple way to compute this value is we initialize p equal to 0. Then in a loop we do this. For I equal to 0 we do this, for I equal to 1 we do this, and we run a loop for I equal to pattern length -1. Let's see what does this mean. After you have done this, your p value is going to have pattern 0, right? And after you have done this, your p value is going to have pattern 0 into D plus pattern 1. And after this, you are going to have pattern 0 into D square plus pattern 1 into D plus pattern 2. Right, I'm simply substituting this value here, multiplying it with D, and that's how I got this expression. And this is the required hash function for a pattern of length 3. And this is the required hash function for a pattern of length 2. This is the hash function for a pattern of length 1. So this is how we compute the hash function for the pattern. And using the same logic, we compute the hash function for the text. So we've computed the first set of hash functions. This pattern hash function is going to be used everywhere in the comparison, and this text hash function is going to be used only for the first window. Now we run a loop for all the windows one by one, and inside this loop, we compare the values of P and T. If these two values are matching, then we compare individual characters. We run a loop for j equal to 0 to m minus 1. We compare the character text I plus j. We are at window I, so we need to shift by I in the text and with pattern j. At any moment, if we find that these two characters are not matching, we set the flag as false and break. If the flag remains true, we found the pattern at shift I. So we print I as part of the result. So this is normal sliding window one by one, sliding over the text one by one, and then comparing the pattern and text. If they match, then we simply print. Now we need to compute the hash function for next iteration. We compute the value of t using the previous value of t. And we use the same function that we just discussed. We are going to subtract this previous window's first character multiplied by h, and then need to add the last character of current window, and we need to do all these computations under modulo q. This is how we compute the hash function for next window of text. And please note that since we have subtraction here, this hash function t value might become negative. So to ensure that we have positive values, because we are going to compare these values here, we add q to it. To ensure that this is a positive value and both positive values compare to equal. Please note that if you have modulo computations, for example, modulo 3 minus 3 modulo 13 is equivalent to minus 3 plus 13 modulo 13, right? So this is 10 mod 13. So what you want is, you want 10 number, you do not want minus 3, because the other number is also positive. You want to ensure that both the numbers are positive, so when you compare them, they remain compared well, right? So that's the purpose of writing this condition, and this whole thing is written for I smaller than n minus 1. The reason is simple. We do not want to compute the next hash function for the last window, right? So we want to stop this computation for last window. That's why we have put this condition. So this is simple code which does pre-compute pattern and text hash functions first, then slides over the text, and for every window of the text, it computes the hash function for next window using the hash function of the previous window. Let us now talk about time complexity of RABIN-KARP algorithm. In worst case, RABIN-KARP's time complexity is same as naive algorithm, and the worst case happens for cases like this. If you see this text and this pattern, what are you going to do? You are going to compare the hash values, and hash values are going to match everywhere. They are going to match here, here, and here. And every time you are going to compare all the characters one by one. So that's how you get this time complexity. So it is like naive algorithm in worst case. In fact, it does more work than naive algorithm in worst case because it's going to require hash function computations. But on average, it works better than naive because you won't have such cases all the time. And if you have large patterns, you are going to skip many character matches that you do in naive algorithm. There exists better pattern searching algorithms like KMP algorithm, which work in linear time. The time complexity is quadratic here. But RABIN KARP algorithm has its own applications. It is used when we want to search multiple patterns in a text. So what we do is we compute multiple hash functions for all the patterns. We slide over the text. For every window, we check if the current hash value falls in or matches with any of the hash functions of the patterns. And if matches, we compare it with that particular pattern. So it is used practically when you have multiple patterns to be searched in a text. Let us talk about this problem. We are given a string. We need to construct longest proper prefix suffix array for this. We are calling it LPS here. This LPS array construction is a prerequisite for understanding KMP algorithm. It's a pre-processing step in KMP. We first construct this LPS array for the pattern. Let us first define what is a suffix and what is a proper prefix. So if we consider ABC as a string, its proper prefixes are empty string, A, AB. Please note that ABC is not a proper prefix. ABC is a prefix but not proper prefix. When we add proper word, it means the length of prefix should be smaller than the given string. What are the suffixes of ABC? Suffixes are empty string, then C, then BC, then ABC. These are the suffixes. Here is one more example to understand proper prefix and suffix better. Proper prefixes of ABCD are empty string, A, AB, ABC, right? ABCD is not included. Proper suffixes of this are empty string, then D, then CD, then BCD, then ABCD. So we are given a string and we need to find out longest proper prefix which is also suffix at every point. So first entry in this LPS array is always going to be 0 because for a string of length 1, you cannot have a proper prefix of length more than 0, right? So your first entry is always going to be 0. Your second entry depends whether these two characters are same or not. If these two characters are same, then it's going to be 1, otherwise it's going to be 0. For example, it's 1 here. Here it's 0, here also it's 0, here also it's 0. The third entry for ABA, what are the proper prefixes of ABA and what are the suffixes of ABA? Proper prefixes of ABA are A, AB and empty string. Suffixes of ABA are A, BA and ABA. So which of them are the longest and same? Only one, A, right? So our output is 1 for ABA. Let us now see the next value. For ABAB, our output is 2. You can notice that the longest prefix AB is also a suffix, so our output is 2. For this ABABC, the last entry for whole string, do you find any proper prefix which is also a suffix? No, so our output is 0. When all characters in a string are same, your LPS array is going to be like this, 0, 1, 2, 3, right? For all characters being distinct, all values are going to be 0. Let's see this example now. Your string is AB, AB, AB. First is always 0. Second is also 0 because the first two characters are not same. Third is 1 because there is a proper prefix which is also suffix. Fourth is 2 because there is a proper prefix AB which is also a suffix. Fifth one is 3 because there is a proper prefix of length 3 which is also a suffix. Sixth one is 4 because there is a proper prefix of length 4 which is also a suffix, right? So that's why we have the output as 4. Now here is an exercise for you to make sure that you understood the question really well. Please write down LPS arrays for this string and this string. Here are LPS arrays for these strings. We have 0 always for the first character, then for second also 0 if the first two characters are not same. In this example, we have 3 characters till this point and our output is 1 because there is a proper prefix A which is also suffix. Till this point, our answer is 0 because there is no proper prefix which is also suffix. For this, we have again answer 1 because A is there. For this point, we have answer 2, AB, AB. For this point, we have 3 answer, ABA, ABA, proper prefix and suffix both. For this point, our answer is 0. Let's see this example. 0 for first 2. For this one also 0 because there is no proper prefix which is also suffix. For this one, we have 1 because A is there. For this one, we have 2 because AB, AB matching. For this one, we have 3. Now, please pause this video and think of a program that takes a string as an argument and builds LPS array for the input string. We are going to talk about 2 solutions for this problem. First is going to be our naive solution with time complexity as big O of NQ, where n is the length of the string. And then we are going to talk about a linear time solution which is used in KMP algorithm. Let us now talk about the implementation of naive approach. Here I have written code. This code is written kind of pseudocode, which is close to C++ and Java programming language. If you're programming in Java, the only thing that you need to change is instead of doing stri, you need to use str.char@I when you are using a string object. Okay, so this function, fill LPS function, takes a string as an argument, an LPS array as an argument, and what it does, it calls the above function for every index, and it uses the returned value of the above function to fill the LPS value for index I. This is the main function. This function takes a string and its length as arguments, and what it does is it simply returns the length of longest proper prefix, which is also suffix for this given string, right? So it works for only one string, and this function calls this function for every substring starting from 0 to n-1. So that's how these 2 functions work. Let us now see working of this function. So what this function does, it's a very basic function. For a string of length n, the maximum value of longest proper prefix, which is also suffix, can be n-1, right? Because you cannot have a proper prefix of length more than n-1. So this function basically tries every length starting from n-1. And as soon as it finds a proper prefix which is also suffix, it stops and returns that particular length. And if it does not find any length greater than or equal to 1, it returns 0 at the end. Now, how does this logic work? This part is explained here. Suppose we have this string to this particular function, right? So what it is going to do, it's going to start from length 7 because the total length of a string is 8. So it's going to try this 7 first, and then it's going to check is 7 a potential answer. So when you are checking for length 7, basically you need to compare this string with this string when you are at length 7, right? So what you need to do, you need to compare str0 with 1, str1 with str2, 0 with 1, 1 with 2, right? That's what you need to compare to check if this longest proper prefix is also suffix or not. For adjusting these indexes, we have written this logic. We compare stri. So these indexes simply go increasing from 0 to len-1, but these indexes grow from n-len. They begin with n-len, then we keep on adding I, where I starts from 0, right? So now we compare these 2 characters, and if we match all the characters, we say that, okay, we found this length as the longest proper prefix, which is also suffix, and we return that length. So these are examples. When you have length equal to 6, you will be comparing, you will be basically be checking this string and this string if length is 6, right? If length is 6, then you will be checking these 2 strings if they are same or not. If length is 5, then you will be checking these 2 strings if they are same or not. You will be checking this string with the last 5 characters of this string. So that's what we are doing in this logic. Now what is the time complexity of the solution? We have 2 functions in it, and this function calls the above function in a loop that runs big O of n times. We are running from 0 to string length -1. And this function has 2 loops, and these 2 loops run big O of n square time, where n is the length of a string. So we have a function being called inside a loop, and this function has time complexity big O of n square. So overall time complexity of the solution is big O of n cube. Now please pause this video and think of a solution that works in big O of n time. And the solution is really tricky. The idea of the solution is to use already computed LPS value. When you are at index I, you must have already computed LPS values from 0 to I minus 1. So rather than computing fresh LPS value for index I, you reuse the existing values and you compute this value using the existing values. Let us now talk about the efficient solution, which is used in KMP algorithm. This efficient solution is based on some basic ideas. This is first basic idea. And this idea is, if we know the length of LPS I minus 1 as length, and if str length and str I are same, then LPS for ith character is length plus 1. So this is our input string, and LPS value for this is length, right? Which means the characters from 0 to length minus 1 are same as characters from here to length, right? So this length and this length characters are same, because LPS means longest proper prefix, which is also suffix. So this prefix is same as this suffix. Characters from this to I minus 1 and having length as length. So this is we know. Now this character and this character, they both are also same. It means your LPS of I is length plus 1. We can simply increment the length by 1. Let's understand this with this example. See, LPS of 0th character is always 0. So our length is initially 0. Now for the second character or index I equal to 1, we simply compare str I and str length. So I is 1. So we compare 1 with str 0. Length is 0. They are same. So we do simply length plus 1 and assign it to LPS 1, which is 1. Now when we are at I equal to 2, our length is 1, right? Because this is the LPS value of 1, right? Now we are at I equal to 2. So we simply compare str2 with str of 1, str of length and str of I. They are same. So we make LPS2 equal to length plus 1, 1 plus 1, 2. And our now length is 2 for the next iteration. When we are at I equal to 3, we again compare str I and str length, which means we compare str3 with str2. They are same. So we make length LPS3 equal to 3 and length also equal to 3. There are no more characters, so we stop this. So using this idea, we could find LPS array for this example string in big O of n time. Now, how do we handle the case when str length and stri are not same? Let us now talk about the case when stri and str length do not match. This particular case has two subcases. The first subcase is len is 0. Please note that this len represents LPS value of index I minus 1, which is longest proper prefix, which is also suffix for your string starting from index 0 to I minus 1. So this is the case. Then there was no matching characters earlier because this is LPS I minus 1 and the current character also does not match with str0. Please note that str length is str0 because length is 0. So if these two are not matching, it means LPS is clearly 0 because this character is not matching at all with this character and LPS of this was also 0. Len is LPS of 0. Right? So this case is really simple. In this case, we simply assign 0 value to LPS I. This is interesting case when length is greater than 0, right? Else part. In this case, we recursively apply the LPS function to find out index of the next character that has to be matched with stri. So we compute the index as LPS of length minus 1. Please remember this length is length of the LPS value for I minus 1 index. So here this length represents the previous value of length, not the updated value. Updated value is this. This is the updated value of length. So let's understand what is the meaning of applying this function recursively and how does this work. This length is length of the LPS I minus 1, right? Value of LPS I minus 1, which means these characters are same as these characters, right? And we were trying to extend this prefix and suffix by comparing these characters, but they did not match. So what are we saying? We are going to now try matching the character at this index. LPS of length -1. That's what we are saying is our new length. Why are we using this index? The reason is these characters must be same as these characters because this is the value of LPS length -1, this particular index. And since this whole thing is matching with this whole thing, this string and this string, they must be same. So this proper prefix must also be a suffix here now. So that is why we try extending this proper prefix now. We try checking whether the next character just after it, the character at this particular index, if this matches with this particular character or not. Because if this matches, then we extend this particular LPS. That's the idea. So if LPS I-1 cannot be extended, then we find the redundancies within LPS len -1 and try extending using those redundancies. Let us now do a complete run of this algorithm for this example. Before we do this run, let's do a recap of the two ideas that we have discussed. The first idea is if stri and str length are matching, then simply do assign length +1 to LPSI and do length ++. Please remember length is LPSI -1, LPS value previous index. If they are not matching, then there are two sub cases. If length is 0, then simply make LPSI equal to 0 because you have already matched 0th character with the current character and they were not matching. So LPS cannot even be 0, right? The second case is when length is greater than 0. In this case, you recursively apply LPS function. You use the value of LPS length -1 and you get a new length. Then you again compare stri with str length. You keep doing it while stri and str length, they are not matching and length is greater than 0. You stop when you see a match or when length becomes 0. Right? So that's a complete algorithm that we run for filling the LPS array. We will be talking about implementation details and detailed algorithm later in this video. Let us first cover this particular example to understand the two cases. We know that LPS 0 is always 0, right? The 0th character is always going to have LPS value 0, so we assign this value and we have initial value for length is 0. Now we are always going to compare stri with str length and then we are going to decide which case we are in. So what is our I now? I is 1. We are computing LPS for this. And what is length? 0. So we compare these two characters. They are not matching. So which case we are in? We are in this case. Length is 0 and they are not matching. So we simply assign it 0. Now we come to this index. Length is 0. And stri and str length, these two characters are not matching. So we simply assign 0 to it, right? Now we come to this index. We again compare stri and str length. These two characters, they are not matching. So we simply assign 0 to this also. Now we come to the next index. We again compare stri with str length. Please note that length has been 0 so far. At this point, stri and str length, they match. So what we do is we assign length +1 to LPS 4 and do length ++. So LPS 4 gets value 1 and length gets value 1. Now we compute LPS 5. When we come to LPS 5, we again compare stri with str length. We compare these two characters. They're matching. So we assign length +1 to this and do length ++. Now we come to this index. And we again compare stri with str length, right? They're matching. So we again fall in case 1. We assign the value length +1 to it and do length ++. Now we come to index 7 and we again compare stri with str length. Length is 3 now and I is this character. So we are going to compare these two characters. They do not match. So this time we see a mismatch after seeing some matches. Your length is greater than 0 and characters are not matching. So you fall in this case 2.b. And in this case, what you do is you find the new value of length using LPS length -1. What is LPS length -1? Length is 3, length -1 is 2. So LPS 2 is 0. So your length is 0 and stri and str length are matching. So when stri and str length they match, you are in case 1. And what we do in case 1? we assign length plus 1 to this and we increment the length by 1. So our length becomes 1. So this length in fact is of no use because there are no more characters after it. We stop at this point and we have computed all the LPS values. Let us now talk about implementation of this efficient approach. I have written a pseudocode here that takes a string as an argument and an LPS array as an argument. This code fills this LPS array for this string. This code is written close to C++ and Java programming languages. What do we do as a first line in this code? We find the length of the string. We initialize the length of previous LPS as 0. And we initialize LPS 0 as 0. Now we run a loop that begins with I equal to 1 and it runs while I is smaller than n. Inside this loop, we are going to first follow idea 1, and if they do not match, then we are going to follow idea 2, and we have two cases for idea 2. So idea 1 says, if str I and str length, they both are matching, simply do length plus plus and do LPS I equal to length and move to the next index. Idea 2 says that if they do not match and if the length is 0, simply make LPS I equal to 0 and make I plus plus. And if length is not 0, then update the length as LPS of length minus 1, which is recursively applying the LPS function again and again until we see a match or length does not become 0. So when I say recursively applying, it means it will keep on going into this iteration, it will keep on falling into this case until we end up falling this case or this case, right? Until the length becomes 0 or the characters do not become same, right? So we'll keep on falling into this case while length is greater than 0. Let's now do a dry run of this example for this particular string. So LPS 0 is always 0. LPS 1, we simply need to compare str length with stri. 0, 1, 1, 0 and 1, they match. So we are going to do length plus plus and assign it to LPS 1, right? So length becomes 1 and LPS 1 becomes 1. Now again str of length and str of I, they match for this I. So we again do length plus plus. We have LPS 2 as 2 and length as 2. Now when we come to I equal to 3, stri and str length, they do not match, right? So we fall into this case and we update the length as LPS of 1. And what do we get as a new length? 1. And again they do not match, right? So we update the length as LPS of length minus 1, which is 0 now. And again they do not match, but this time length is 0. So we make LPS of 3 as 0. Now we come to I equal to 4 and this time stri and str length, they match. So we make length equal to 1 and make LPS 4 equal to 1. This time again they match, So we keep on incrementing length and LPS. When we come to I equal to 7, they do not match. We are matching str of length, which is str of 3 with 7a, right? So they are not matching. And now length is greater than 0. So we fall into this main case again. And what do we do now? We make length equal to LPS of length minus 1, LPS of 2, which is 2, right? And now we again match. And this time, this and this, they match, right? So we simply make LPS of 7 equal to length plus plus, right? And length now becomes 3 and LPS 7 also becomes 3. Now we move to I equal to 8. When we come to I equal to 8 case, our length is greater than 0 and the characters do not match, right? The character at LPS length is 3 now, they are not matching, right? So we fall into this case again and we update the length as LPS 2 and str2, it again does not match with this character. So we again update the length as LPS 1, again do not match. We update the length as LPS 0. Again, they do not match. This time we fall into this case and we make LPS of 8 as 0. So this is how we compute LPS array for this particular string example. Let us now talk about time complexity of this. Let's consider some corner cases first. What happens when all the characters are same? When all the characters are same, you are always going to fall into this case and you are always going to do I plus plus, right? So your time complexity is clearly theta n, because I begins with 1 smaller than n and always do I plus plus. Now let's talk about the case when all the characters are distinct. In this case, you are always going to fall into this case. Your LPS value is always going to be 0 and you are always going to do I plus plus. So this also needs theta n time. Now let's talk about the case when some characters matched and then there was a mismatch, when you have to execute this part. Like this example, these A's were matching, then there was a mismatch. These A's were matching and then there was a mismatch and then there was one more match. This particular case, when you fall in, it needs at most 2n work. You did X matches, right, or length matches. Then when you see a mismatch, you will again do at most the length matches again. So you did traverse n characters, and at the most you are going to traverse all the n characters again. So overall, the time complexity of this particular solution is theta n. When you fall in this case, you may need 2n work, but this is also theta n. Hi, in this video we are going to talk about KMP string matching algorithm. So the problem is we are given a text and a pattern. We need to find out where all this pattern is present in the text. In this example, pattern is present in index 1, right? This is index 0, this is index 1, and your whole pattern is present here. So our output is 1. Let's see this example. In this example, our pattern is 4A's and our text is 5A's followed by B. So pattern is presented at index 0, right here, and also presented index 1 here. So our output is 0, 1. In this example, the pattern is not present. BA is not present at all, right? So our output is not found. We have already talked about some algorithms to solve this problem. We talked about naive algorithm, which is quadratic in time. Then we talked about naive algorithm for distinct characters. If your pattern contains distinct characters, then you can optimize the naive algorithm to work in big O of n time. Please note that n is the length of text here and m is the length of pattern here. Then we talked about RABIN KARP algorithm, which is also quadratic in worst case, but RABIN KARP algorithm works better than naive in general. RABIN KARP algorithm uses the idea of rolling hash. In this video, we are going to talk about KMP algorithm. KMP algorithm takes big O of n time and requires big O of m auxiliary space, where m is length of the pattern. The main idea of KMP algorithm is to pre-process the pattern and then do the pattern searching. And KMP algorithm does pattern searching like naive algorithm. It slides the pattern over the text one by one and then finds all occurrences of the pattern. When we will do the time complexity of KMP algorithm, we'll see that it does at most 2n work. The loop inside KMP algorithm does at most 2n time, where n is the length of text. In this example, naive algorithm first started with window at shift 0, did 4 comparisons, then shifted the pattern by 1 and again did 4 comparisons, then shifted the pattern by 2 and again did 4 comparisons. So how many comparisons naive algorithm did here? 4 plus 4 plus 4, 12, which is n minus m plus 1 into m in the worst case. That's the worst case number of comparisons that your naive algorithm is going to do. Let us now get an idea of KMP string matching algorithm. How KMP is going to work better than the naive for this particular example. In KMP algorithm, we first pre-process the pattern and build an array called LPS. The size of this array is same as the size of this pattern. There are 4 characters in the pattern, so this array is of size 4. And this is an integer array. LPS ith element in this particular array stores the longest proper prefix of pattern from index 0 to I, which is also a suffix of the same pattern here. We have discussed LPS computation in detail in the previous video. How do we get these values and how to fill this LPS array in linear time. Let us now see how KMP algorithm uses this LPS array to find the pattern. Like naive algorithm, KMP also begins with I equal to 0 and j equal to 0. J is going to be an index in the pattern and I is going to be an index in the text. It matches text I with pattern j in every iteration. And here they match. I is 0, j is 0, so they're matching. Now we increment both I and j. We come here and we match these two. So I is now 1 and j is now 1. So I is here and j is here. So they are matching again. So we again increment I and j. This is similar to naive algorithm. what we're doing here is same as naive algorithm. They are matching again. Now we again increment I and j, so they're matching again. So we come here, right? And now we see that we have matched all characters of the pattern with all characters of the current window of the text. So we say that we found the pattern at index 0 and our output is going to have 0 as the first thing. We are going to print 0 as the first occurrence of the pattern. Now the question arises, what should be the next characters to be matched? We have matched all the characters. What were we doing in the naive algorithm? We were going to compare this character and this character in the naive algorithm. And this is where KMP algorithm does optimizations using this LPS array. What it does is, it looks up the value for the last matched character in the LPS array. Last matched character is the last character, right? Last character of the pattern. So this particular LPS value is looked for finding the next indexes to be matched. This value is 3. So the index of the character that we need to match in the pattern is 3. This is the next character that we need to match in the pattern. And in this particular text, we always increment the index by 1 whenever we see a match. So our next characters to be matched are this and this, right? In text, the rule is simple. Whenever you see a match, you always increment the index. In pattern, we use the LPS array to find the next index. And we got the index as 3. So next time, we are going to match these 2 characters only. We are not going to match all the 3 characters. This LPS array actually tells us that these 3 characters are anyways going to match these 3 characters, and there is no point matching them unnecessarily. And with the help of LPS array, we save all these 3 comparisons, and we are going to mainly compare this character with this character next time. And how did we get the index of this character? We used LPS value for the last matched character. Now let's understand how does this LPS array helps us in skipping these 3 matches that we were doing in the KMP algorithm. What is the meaning of LPS? LPS means at this index, which is the index of last character, which means here the length of the proper prefix, the longest proper prefix, which is also suffix, is 3, which means these 3 characters are same as these 3 characters. They are same, right? They are same as these 3 characters. This is longest proper prefix length 3 and this is suffix also 3. And now if we leave this LPS array for some moment and if we take a look at the pattern and text KMP algorithm, why did we consult the LPS array? Because these 3 characters had matched these 3 characters, right? So these 3 characters are same as these 3 and these 3 are same as these 3 because of LPS array telling us, right? Which means they are going to be same as these 3 characters because they are same as this and they are same as these. They are same as these is told us by LPS array, and they are same as these we figured out because we were running the KMP loop and we were matching the characters one by one. So that is how we skip matching these 3 characters with these 3 characters. We do not have to match them. We just need to match these 2 characters. Why are we not matching these 3 with these 3? Because they will anyways match. You know, LPS array is telling us that they will match. No need to match them again unnecessarily, right? So we simply match these 2 characters. We find a match, and since this is the last character of the pattern, at this moment we simply print output as 1. We found the pattern at shift 1. Now again, which character should we match? We again consult the LPS array. And LPS array tells us that LPS value of the last matched character, which is A, is 3. So you again need to match the last character of this with the next character in the text. Next character in the text is B. Now you are going to slide the pattern this way, right? And you are going to match this A with this B, right? And this LPS array tells that you do not need to match these 3 characters with these 3 characters. They will anyway match. No need to match them again unnecessarily, right? And since they do not match, you do not print this particular shift as part of output. Please note that naive algorithm also works in linear time when all the characters in the pattern are distinct. It starts taking more time when there are redundancies within the pattern. And that's the whole idea of KMP algorithm. It pre-processes the pattern, which is basically it pre-processes the redundancies within the pattern so that the worst case time remains linear. Let's now take a look at detailed algorithm. So we have written code here, which is a pseudocode close to C++ and Java programming language codes. We are passing two strings to this function, pattern and text. As a first step, we are finding their length. N is the length of text and M is the length of pattern. After that, we build an auxiliary array, LPS, and we fill this array using the fill LPS function. We have talked about this function in detail in the previous video. So this is all pre-processing part. Now begins the comparison part. We initialize I equal to 0 and j equal to 0. And then we run a loop while we have not reached the last character of text. Inside this loop, we keep on incrementing I and j if pattern j matches with the text I. And if we matched all the characters, if j became m, then we print the shift as I minus j, right? Or you can write I minus m also, because I is the current character and you will find the beginning of this shift by doing I minus m. And then we use LPS array to find the next value of j, right? That is something we discussed and checked in the previous example. If the current characters do not match, then we have two cases. If j is 0, if it was the first character that we were trying to match and this first character itself did not match, then simply move ahead in the text. Simply do I++. And this is the case where there were some matches and after some matches there was a mismatch. So we do same as we did here. Whenever see a mismatch after matches, we consult the LPS array to find the next character in the pattern to match, right? So this is the trickiest part here and here. They both are same. And this also is the case when you have already matched certain characters. In fact, you have matched the whole pattern and now you are trying to find out next value of j after certain matches. And this is where also you are trying to find out the next value of j after certain matches. If you take a look at this algorithm, it looks very similar to what we discussed in this fill LPS function in the previous video. Fill LPS also uses the idea of this KMP algorithm to fill the LPS array. Let's now do a dry run of this algorithm for this particular example. So this is our text and this is our pattern. Length of this text is 12 and length of the pattern is 5. And we have built LPS array for this particular pattern. And now we are going to begin with I equal to 0 and j equal to 0. Right? So we are here in this algorithm. And inside this loop, we compare pattern j with text I. So we compare the first characters. They're matching. So as long as the characters are matching, we keep on doing I++ and j++. Matched, we came here. We now have I equal to 1 and j equal to 1. So they also matched. Now we have I equal to 2 and j equal to 2. They also matched. Now we have I equal to 3 and j equal to 3. They also matched. Now we have I equal to 4 and j equal to 4. And when I is 4 and j is 4, they do not match. Right? So we come into this case that characters do not match. And which case we are in this particular case? There are two cases in this. J is not 0, right? So we are in a case when we have seen a mismatch after certain matches. So we consult the LPS array to find the next value of j. And to consult, we go to the index of last matched character. Last matched character is j is 3. So at j equal to 3, we have 2 in the LPS array. So j now becomes LPS of j minus 1, which is 2. Right? So we have this j as 2. We have brought the pattern here. We did not change I. We simply changed j equal to 2, which means the pattern has come here. These two characters need to be matched now. Right? So this is our current I and this is our current j. Right, j is 2, and I just brought this pattern such that j equal to 2 comes just before the current I. Now we are again going to compare these two characters, and these two characters again do not match. So we are going to consult the LPS array to find the next shift, and last matched character was this one, so we are going to get the j as LPS of j minus 1. So j minus 1 is 1. J was currently 2. So LPS of 1 is 0. So this time we are going to bring this character a below it, and then we are going to compare them. Now I have written the 0th character below current I, right? And now we are again going to compare them, and they do not match. If they do not match, we have two cases, and this time we are in this case because j is 0. So what do we do now? We increment I. We bring I equal to here, right? And we do not change j. J remains 0. So next time we are going to compare these two characters. So now we are at I equal to 5 and j equal to 0. I have rewritten all these steps for your reference. We started with I equal to 0 and j equal to 0. They were matched, so we incremented I and j both. Then again matched, so we incremented I and j. Again matched, we incremented I and j. And this time they mismatched, right? So we saw a mismatch at I equal to 4 and j equal to 4, right? And at this point, we consulted the LPS array to find the next j, and we found the next j as 2, and we compared text of I and pattern j again, and they did not match. So we again consulted LPS array and we found j equal to 0, and we kept I equal to 4. And at this point, we again found a mismatch, but this time j was 0, so we changed I. Now we are here at I equal to 5 and j equal to 0. Now we see a match, right? So we are going to increment I and j both. Now I is going to become 6 and j is going to become 1, right? So I and j are changed. They are here right now. Now I and j again match, so we are going to make I equal to 7 and j equal to 2. They again match, so we are going to make I equal to 8 and j equal to 3. They again match, so we are going to have I equal to 9 and j equal to 4. And they also match, so we are going to have I equal to 10 and j equal to 5. So j now becomes m, which is the number of characters in the pattern. So we fall into this particular case and we print I minus j or I minus m, because j is m right now. So what is I minus j? 10 minus 5. So we are going to print 5. We are going to tell the output that we found the pattern at index 5, and you can notice that this pattern is presented at this index, which is 5, 0, 1, 2, 3, 4, 5. So we print 5 on the screen. After printing 5 on the screen, we again consult the LPS array for next value of j. Now we need to find out LPS of j minus 1, which means LPS of 4. What is LPS of 4? 0, 1, 2, 3, 4. It's 3. So we are going to have j equals to LPS of 4, which is 3. Let's now shift according to new I and j values. Now I have aligned I equal to 10 with j equal to 3. And this time we again see a mismatch. So what are we going to do? We are going to consult the LPS array and we are going to look at LPS of j minus 1, which means LPS of 2. LPS of 2 is 1. So our j now becomes 1. Now let us align first character with I equal to 10. Here I have aligned I equal to 10 with j equal to 1. These two characters again do not match. So we are going to consult the LPS array. We are going to look at LPS of j minus 1, which is LPS of 0. And LPS of 0 gives us 0. So we are going to make j equal to 0 now, and we are going to keep I as 10 only. Now I have aligned for I equal to 10 and j equal to 0. At this point, they are matching. So we do I plus plus and j plus plus. Our new I becomes 11 and j becomes 1. and we see a mismatch. These two do not match. I equal to 11 and j equal to 1. They do not match. So what are we going to do? We are going to consult the LPS array, right? We are going to find out LPS 0, which is a 0 value. So we are going to update j as 0 and we are going to keep I as 11. Now I have aligned for I equal to 11 and j equal to 0. So this is our text and this is our pattern. Text is at I equal to 11 and pattern is j is equal to 0. So we are again going to compare text I with pattern j, and this time they do not match, and this time we have j equal to 0. So what are we going to do? We are going to make I equal to 12. Now when you make I equal to 12, the loop will not run again because I should be smaller than n. And at this point, KMP algorithm stops. Let us now talk about time complexity analysis of KMP algorithm. If we take a closer look at this loop, we can notice that in every iteration, we are moving ahead in the text or we are sliding the pattern ahead. When you do I++, j++, you are simply moving ahead in the text one by one. And when you do any of these two operations, this or this, you are sliding the pattern ahead. For example, here j was 2 and you changed to j equal to 0 using this thing that they are not matching, so you change it. And what it effectively means is you slided the pattern 2 positions ahead, right? And you're sliding this pattern over the text. So how much maximum you can slide? You can slide it at most n times, right? You begin with from here, then you slide here maybe, and then slide here. Even if you are sliding one by one in the worst case, you will slide at most n times. And how much you can traverse in the text if you are doing I++? It's the length of the text. Your I begins with 0 and then you go up to n-1. So you are doing n work for traversing through the text and n work for sliding the pattern over the text. So overall work done by in this KMP algorithm is upper bounded by 2n, where n is the length of text. Let us talk about this interesting problem. We are given two strings. We need to check whether they are rotations of each other or not. We basically need to check if a string s2 can be obtained from string s1 by rotating s1 any number of times. We can either left rotate it or right rotate it any number of times. Let's see these examples to understand the problem. Let's say ABCD is our s1, s2 is CDAB. If I rotate s1 2 times counterclockwise, then I'll get s2. First time I rotate, I move from A from here to here, I get this. Next time I rotate, I move B from here to here, I get this. Same thing I can get by rotating clockwise as well, right? If I rotate it clockwise, I'll move D here, then I'll move C here, right? So I'll get CDAB. In this example, S2 is obtained from S1 by doing one counterclockwise rotation. I have moved A from here, and I can obtain S2 by doing 4 clockwise rotations also. I move this A here, then I move this A, then I move this A, then I move B. So I'll get this, right? So if you're doing X left rotations or counterclockwise rotations, you can get the same string. If you're getting a string, then you can get the same string by doing n minus x clockwise rotations, right? In this example, these two strings are not rotations of each other. You can see by rotating string s1 any number of times, you will not get s2. If you rotate it once counterclockwise, you will get BA, BA. If you rotate it twice counterclockwise, you will get AB, then you will have AB, right? Then if you rotate 3 times, then you will have B, then you will have A coming here, then B coming here, then A coming here. This is what you will get after 3 rotations. So you never get this string. So these two are not rotations of each other. Now please pause this video, write down a function that takes 2 strings as an argument, returns true if the given 2 strings are rotations of each other, otherwise returns false. A naive solution to solve the problem is to try all n rotations one by one. So if string s2 is a rotation of s1, you can get s2 by rotating s1 n times one by one. First you rotate 1 times counterclockwise, then you check if it becomes same as S2. Then you rotate 2 times counterclockwise, then you check if it becomes S2. Then you rotate 3 times, then you rotate 4 times. So this solution is definitely going to take n square time, because you will be rotating n times one by one, and then you will be comparing two strings, right? So it's going to take n square time. Please note that this solution can be implemented two ways. You can either rotate n times counterclockwise, or you can rotate n times clockwise. Both ways you can get the answer, because every counterclockwise rotation is equivalent to a clockwise rotation. So this is an n square solution. Can you solve this problem in big O of n time? Let us now talk about an efficient solution. If you take a closer look at this problem, it's similar to pattern searching algorithm. We need to consider S2 as a pattern and S1 as a text, and we need to search S2 in S1 in a circular way. For example, if I want to search this in this, I can search C here, and then I can match D, and then it's the end of S1, so I'll go in a circular way. Then I'll match A with A, B with B, right? So I found S2 in S1. So I'll say S2 and S1 are rotations of each other. Similarly, if I try this example, the second example, I'll search for S2 in S1. I'll search for A, then I'll match for B, then I'll see a mismatch. So I'll not say this is a match. Now I'll look for next A and A match, B and B match. Now I'll go in a circular fashion, B and A do not match. So this occurrence of A is also not matching. So one solution is to implement our own pattern searching algorithm. Either implement naive searching algorithm, but that will be quadratic, or modify the KMP algorithm implementation ourselves and then implement in a linear time. But implementing KMP algorithm or any linear time algorithm would be a complex task. Here is a very simple implementation that's also a linear time solution. The idea is to concatenate S1 with itself. So instead of going in a circular way, we concatenate a string S1 with itself, and then we use standard library functions which work in linear time. So what we do is we concatenate S1 with itself. So S1 now becomes ABCD, ABCD, and now if you search S2 in it, and if S2 is a rotation of S1, then it must be present in the S1 string concatenated with itself. So S1 plus S1 is ABCD, ABCD. Now if you search S2 in it, it's present here, CDAB. It is same as pattern searching algorithm in a circular way. Instead of going in a circular way, what I have done here is I have concatenated S1 with itself so that I can use standard library functions. Now if you see this example, I concatenate S1 with itself, I get AB, AB, then AB, AB again. Now if I search for A, B, B, A in it, I won't find it, right? It's not there, so it's not a rotation. So this is how we implement this tricky approach in 2 lines. In fact, we can reduce it to 1 line by putting AND condition here, but it's 2-line implementation. The first thing that we check here is if S1 and S2 lengths are not same. If they are not same, then we return false. We check the next thing only when they are same, right? 2 strings have to be rotations if their lengths are same. And if lengths are not same, we return false. And if lengths are same, then we come here. And here what are we doing? We are concatenating S1 with itself. We are concatenating S1 with itself, and then we are searching S2 inside it using find function in C++ and using index of in Java. So index of function returns index of S2, index of first occurrence of S2 in S1 in this string S1 plus S1. And if it's not present, then it returns a negative value. So in Java, we simply call index of, in C++, we simply call find function. And find function returns a special constant string : npos if the string that you are searching is not present. Otherwise, it also returns index of the first occurrence. So we have 2 lines of code to check 2 strings are rotations of each other or not, and time complexity of the solution is also linear, because concatenation will take linear time, and then searching a string in another string by these standard library functions also is a linear time solution. So this is a theta n solution, and it takes theta n auxiliary space because we are concatenating the string with itself to create a temporary string. Let us see this problem. We are given a text and a pattern. We need to find if pattern is present in the text or any of its permutations is present in the text. So when we say permutation, two strings which are permutations of each other are also called anagram. So we need to check if pattern is present or an anagram of this pattern is present in the text. Let's understand the problem with these examples. Say our text is Geeks for Geeks and our pattern is frog. So if you look for frog and its permutations in the given text, you will find that FORG and FROG, they are permutations of each other. So our output is yes, it's present, its permutation is present. Now let's see this example. We have this text and we have this pattern. Do we have permutation of this pattern in the text? See, we have these characters E, E, K, S. We also have these characters here, and we also have R, but they're not contiguous. We have a G in between, right? So the answer is no. We do not have a permutation of the string present in the given string at contiguous locations, right? So there should be a substring which should be anagram of the given string. We can't take the non-contiguous characters. Now please pause this video and try to write a program that takes a pattern as an argument, a text as an argument. It returns true if the pattern is present or any of its permutations is present. Otherwise, it returns false. Let us first talk about the naive solution to solve the problem. Here we have C++ implementation and this side we have Java implementation. Let's say we have this text and this pattern. What we do here is we slide this pattern over this text one by one. We first bring frog here and then check if they are anagram. Then we slide the pattern here and then check if they are anagram. Then we slide here and then check if they are anagram. That's the simple idea. And this code is just anagram checking code, right? You can ignore this code. We have already discussed anagram checking in an earlier video, so you can ignore these functions are anagram. They're simply checking if the two things are anagram of each other or not. It checks if pattern and text beginning from I, they are anagram of each other or not. If they're anagram, it returns true, otherwise it returns false. Now, if you take a look at these main functions, they are very similar to naive pattern searching. We are finding the length of the text, then we are finding the length of the pattern, and then we are sliding the pattern over the text one by one. We begin with I equal to 0 window in the text, right? And we go till n minus m. So here your pattern length is 4 and text length is 13. So till which index you are going to go? You are going to go till this index, and this index is 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This index is 9. Till this index you will go. So you go through every index and then you check if the text at the current window and pattern they are anagram of each other or not. If they are anagram, you immediately return true. And if you never found an anagram, then you return false. Now let's talk about time complexity of this solution. This solution clearly requires big O of n minus m plus 1, right? These many times this loop will run the worst case into m, where m is the length of the pattern. This is the time required by the solution. I am assuming that alphabet size is constant, so I'm not counting this char in part of my computations. Char is 256 here. In C++ you can define a char, and similarly in Java you can define a static final variable with value 256. So I'm not considering char. This is the time complexity we get, and if we do not consider char, we can say auxiliary space is also big O of 1. Now please pause this video and try to think of an approach that takes linear time, works in linear time to find if an anagram of a string is present in a pattern or not. Let us now talk about an efficient solution to solve the problem. This efficient solution is similar to the naive solution. It's basically an optimization over the naive solution. The idea is same. We are going to slide this pattern over the text one by one, and then we are going to compare if they are anagram. The current window of the text matches with the pattern or not. So how do we do this? Here in the earlier solution, naive solution, what we were doing, we were sliding and then we were calling R anagram function for every slide. And R anagram function was computing the frequencies of every character in the pattern and computing the frequencies of all the characters in the current window of the text. And if these frequencies were same, then it was returning true, otherwise it was returning false. So the optimization that we do here is at the R anagram function. We don't call this function anymore. What we do here is we slide the pattern like the naive solution over the text one by one. So first we have the pattern here, and we have initially computed counts of characters in the first window of text and the pattern, right? So this is what we do in the first loop. We have a frequency count array for text, count in text CT, count in pattern CP. We have initialized both these arrays as 0. So char is a constant here, which is 256, right? In Java, you can say char is a static final variable, which is 256. In Java, both CT and CP arrays are initialized as 0, 0. So we have first initialized the count arrays. Now we have computed the counts of characters in the first window of text, which are these 4 characters, and full pattern, these 4 characters of the pattern, right? 4 characters of the text. And this is initial count that we have for text, and this is initial count array that we have for pattern. For G we have 1 occurrence, for E we have 2 occurrences, for K we have 1 occurrence. For F 1, G 1, O 1 and R 1. So this is similar to naive method that you first compute the frequency and then you check whether they match or not. Now the different thing that we do here is the optimization that we do here is over the naive method. When we slide the window to the next window, right? When we move from this window, previous window was this one, first window, and our next window is this one. When we slide the window, we just have to remove this character and add this character. And for that, we can simply go to the count array and reduce the count of G by 1, 0 and add the count of S. So we add the count of S here, 1, right? That's all we need to do. And this is big O of 1 operation. And that's the trick here, sliding window trick. When you slide the window in the text from previous position to next position, you just need to remove the first character of previous window and you need to add the last character of the current window. So we added S and removed G when we came from here to here, right? Now when we move to the next window, our next window is this one, right? And our previous window is this one. What all we need to do is we need to reduce the count of E by 1 and we need to add the count of F by 1, right? So E's count becomes 1 now. And F's count become 1, right? So F would come here and its count is 1 now. So that's our new frequency array. We compare these two frequency arrays again and then we check if they're same or not. Let's now take a look at the implementation. In the implementation here, first thing is we compute the count for both the arrays, right? Both the first window of text and pattern, right? After we have computed the initial counts, we are sliding the window one by one, and before sliding the window we are checking if the current counts are same. Here is the function rsame. I have not written implementation of this function. This function simply checks whether the contents of these two arrays CT and PT they are same or not. This is as simple as that. If CT and PT have the same values, then it's going to return true, otherwise it's going to return false. So we check the current counts. If the current counts are same, then we return true. Otherwise, we remove the previous window's first character. This is where we remove the previous window's first character. How do we find out? I is the index of last character of the current window. We go to the previous window's first character using I minus pattern length. We go to that index, right, in the text, get that character and reduce the count of that character by 1. Same as in Java. We have caret function in Java instead of square brackets. We go to that index, that character at that index, and we reduce its count by 1. And we are adding the last character of the current window, text.caret I plus plus. So we add the last character, remove the previous character, remove the first character of the previous window. And at any point, if we find CT and PT are same, we return true. Let us now talk about time complexity of this implementation. So we run this loop which runs for pattern length time. We are doing constant work inside it. So it's big O of m work if m is the length of the pattern. So this is big O of m work, or we can say theta of m work. It's always going to take m time. Now inside this second loop, we run it n minus m times because we begin from pattern length and go to the text length. Here m is the pattern length and n is the text length. So this loop runs n minus m times. Right, inside this loop, we are checking if these two characters and if these two arrays CT and PT are same or not. If these two arrays are same, then we return true. So this work is going to take theta of char time, right? Because you have char sized array and you're checking if these two arrays are same or not. So if we want to be precise, we can say time complexity is theta of m work in the first loop plus n minus m into char. That's the, or we can say big O, because you may return somewhere in between into char. That's much work we are doing in this function. So I've simplified this time complexity because I can say this is m into char upper bounded by m into char, and then we can say n into char because m is smaller than n, right? So I can say it's n into char. That's the simple form of the time complexity. Auxiliary space it requires is big O, theta of char, because there are char character, two arrays of size char characters. Now if we consider char as a constant, consider all the ASCII values or only lowercase alphabets or in uppercase alphabets, then you can say its time complexity is linear and auxiliary space is big O of 1 or theta 1. Let us talk about this problem. We are given a string, we need to find lexicographic rank of the given string. Let's understand lexicographic rank using pen and paper method. Let's say the given string is BAC. To find the lexicographic rank of BAC using pen and paper, what we do is we first sort all the characters of BAC, so we get ABC. Now we generate all permutations of these three characters in increasing order, in lexicographically increasing order. So first permutation ABC, second is ACB, third is BAC, BCA, CAB and CBA. And all these permutations are written here in lexicographically increasing order. Now we see is where does this string BAC fit in? So BAC is at the position number 3. That's why BAC's lexicographic rank is 3. Let's see the next input, CBA. CBA comes at the last position among all the permutations. So lexicographic rank of CBA is 6. Now DCBA, if you see DCBA, it contains 4 characters and there are factorial 4 permutations, 24 permutations, and DCBA is going to be the last string in these permutations, right? So lexicographic rank of DCBA is 24. Now what will be the lexicographic rank of ABCD? It's going to be 1, right? Among all the 24 permutations, ABCD is going to be at the first position. Now we'll shortly see how do we get the number 598 for a string. The method is same. You sort the characters, right? You put G first and then I and then next increasing character, then generate all the permutations of these characters, then see where does this string comes in at what position. That position is actually 598. Now please pause this video and think of an approach that takes a string as an argument and returns an integer value which is lexicographic rank of the string. Let us first talk about a naive solution to solve the solution. A naive solution is simply to follow this pen and paper method. We generate all the permutations of a given string in increasing order. While generating the permutations in increasing order, we compare the permutations with the given string, and if any permutation matches with the given string, we return the count of permutations that we have generated so far plus 1, or we just keep on incrementing the count, right? So that's one way of finding lexicographic rank of a string. Now what will be the time complexity of the solution? See, there are going to be factorial n permutations for a string of length n, and you are going to compare every permutation with a given string. So in the worst case, like this string, when your given string is last in the all permutations, in the worst case you will generate all factorial n permutations and you will compare every permutation with a given string, and given string length is n. So you are going to take n into factorial n time at least in the worst case. That's the worst case time complexity of this naive solution. We have a solution that works in linear time. Now please pause this video and think of a solution that finds lexicographic rank of a string in linear time. Let us first talk about the idea for the efficient solution with this example. Let's say we have this example string. So the main idea is to count smaller strings, count lexicographically smaller strings and add 1 to it. That's your result, right? If you know how many strings are lexicographically smaller than this and you add 1 to it, you get the rank of this string. Now how do we count lexicographically smaller strings than given string? For that purpose, we traverse through string from left to right, and for every character what we do is we see how many characters are smaller than this on the right side, right? Because if we replace that character from those smaller characters on the right side, we will get a lexicographically smaller string, right? So we begin with character S. How many characters on right of S are smaller than this? 4 characters, R, I and G. So if I replace S with any of these 4 characters, I will get a lexicographically smaller string. How many lexicographically smaller strings I will get if I put the first character as R? 1, 2, 3, 4, 5, factorial 5 strings. Similarly, if I replace S with I, I'll get factorial 5 more strings. So the count of lexicographically smaller strings that do not contain S as a first character is 4 into factorial 5. 4 characters are smaller and 5 places are to be filled with remaining 5 characters. So this is about the first character. Now we have counted all the lexicographically smaller strings that do not contain S as a first character. Let us now count all those lexicographically smaller strings that contain S as a first character. For that, we can't now move S. Now we go to the second character and we repeat the same process. We count how many characters on right of T are smaller than T, and we again get 4. So we can replace T with 4 characters, and then we can have factorial 4 permutations for every character because we have 4 places left after it. There are total 6 characters in this string. So we have 4 in place of T. If I put in place of T 4 smaller characters, I'll get these 4 different prefixes, and for every prefix I will have factorial 4 strings. So I have 4 into factorial 4. So now I have counted all the strings that begin with S but do not begin with T. Now I am going to count the strings that begin with S and T. So these are the strings that begin with S and T. Now we have the third character R, and we count how many characters on right of it are smaller than this, right? So right of R, we have 3 characters, all 3 are smaller. So we have 3 into factorial 3. We can replace R with I, with N, with G, and then we can have 3 factorial 3 permutations. So this is the count we get when we replace R with the smaller characters. Now we fix the next character. We fix the character R and we count how many characters are smaller than our next to R character, which is I, right? Because if I replace I with the smaller characters, then only I'll get lexicographically smaller strings, and my task is to count lexicographically smaller strings. So I can replace I with G. There is 1 character. That's why we have 1 into factorial 2. We replace I with G, and then we have factorial 2 permutations, right? So 1 into factorial 2. Now we go to the next character in the same way. Next character is N. And how many characters are smaller than N? Only 1 character, G. Smaller than N on right of N, right? Right of N is important because previous characters we have already counted, right? We have counted strings that don't begin with S, strings that begin with S but don't begin with this, right? So we only need to count on the right side. On right of N, we have 1 character and this is smaller. So we can replace N with G, but we have only 1 place left to be filled. So we have 1 into 1 factorial 1 permutations that we get with this setup. So these are all counts of lexicographically smaller strings, right? And if I add these count, I get 597. So 597 strings are lexicographically smaller than this. Then what will be the rank of the string? It will be 597 plus 1, right? Count of lexicographically smaller strings plus 1. So we use this idea to count lexicographically smaller strings, 597 strings, and then we add 1 to it. So our result is going to be 597 plus 1, which is 598. Now you have enough idea how do we get the lexicographic rank of this string. Please pause this video and try to implement this approach in big O of n time. Let us now see one more example to get better idea of the problem. We have say string DCBA. We know this rank is 24. Now how do we get 24 using this method? We process all the characters from left to right. For D, we count how many strings are smaller than this. For that, we count how many characters on right of D are smaller, right? So there are 3 characters, A, B, C. We can replace D with all these 3 characters and we get 3 into factorial 3 permutations of strings which are smaller than DCBA and do not contain D as a first character, right? Now we need to count the strings which are smaller than DCBA and contain DCBA as a first character. So these remaining are those strings. Now we fix D and then we check for C, same process. How many characters on right of C are smaller than C? 2 characters. So we put 2, then we have factorial 2 permutations for everything. So 2 into factorial 2. Now for B, we have 1 character smaller A and factorial 1 permutation plus 1 into factorial 1, which is 1. So we get 3 into 6, 18 plus 4 plus 1, 23. These many strings is smaller plus 1 is equal to the rank of this DCBA. 23 strings are smaller than this, so its rank is 23 plus 1, 24. Let us now see implementation of the efficient approach. In this implementation, we are assuming that all characters of our input string are distinct. However, you can easily extend this solution with duplicate allowed strings as well. So if you remember the solution that we just discussed, the idea was to traverse the string from left to right. Say this is the string, we traverse it from left to right. For character S, we count how many characters on right of it are smaller than this. So we saw 4 characters, then we multiplied 4 with factorial 5. Right? When we came to T, we counted how many characters on right of it is smaller. There are 4 characters. We multiplied this 4 with factorial 4. So we need a factorial value in every iteration. In the first iteration, we need factorial 5. In the next iteration, we need factorial 4. In the next to next iteration, we need factorial 3, then factorial 2, then factorial 1. For that purpose, what I have done here is I have pre-computed factorial. So I have not written code for factorial. I assume that you all can write the factorial code. So there is one factorial function that I have already computed. I have computed factorial 6, pre-computed it for the string. Now inside this loop, if you see, I am dividing factorial, pre-computed factorial by n minus I. So in the first iteration, I'll divide it by 6, right? So I'll get factorial 5 and I need factorial 5. In the next iteration, I'll divide it by 5. So I'll get factorial 4, right? So I'm dividing by n minus I, n minus 0, which means n minus 1, which means n minus 1, right? So first divide by 6, then 5, then 4, and so on. So this is how we get the factorial in big O of one time. Now, how do we get count of smaller strings on the right side in big O of one time? To get the counts of smallest characters on the right side, what we do is we use a count array. We initialize a count array with all zeros. This is C++ initialization with all zeros. In Java, it's by default initialized as 0, so we don't need an explicit initialization. After initialization, we count frequency of every character, and I said I'm assuming that all characters are distinct, so frequency will be at most one, right? So we have 1 for G, 1 for I, 1 for N, 1 for R, S, T, right? So this is our count array after this first for loop. After we have computed the count array, we compute cumulative count for every index, right? So index I means sum of all the counts from 0 to I minus 1, and to do that, we do count I equal to count I minus 1 plus count I. Why are we doing all this? The purpose is to get counts of smaller characters on right side in big O of one time. We'll shortly see how does this help in getting this count. So now for every character, I have counts of smaller characters than it in the whole string. For example, if you see T, I can get the counts of smaller characters than T in the whole string as 5. I just need to go to index T minus 1, which means S, and I get the count as 5. There are total 5 characters smaller than T in the whole string. There are total 4 characters smaller than S in the whole string. So I can easily get this count. Now you must be wondering, like, this tells me the overall smaller character count. How do I get the count of characters on the right side? So the trick that we here use is we traverse the string from left to right, and when we have processed a character, we remove it from the count array. So when we come to a character, we have already removed the left character, so whatever we have is count of smaller characters on the right side only. So what we do is we begin with S, right? And we first compute like how many characters are smaller than this. We get it using stri-1. In Java, str.char at I-1. We get counts of smaller characters, we multiply it with the multiplier that we just discussed, right? Which is, for example, 5 here for the string. After doing this, we update the count array. And to update the count array, we use this character as an index. We go to the right side of it and reduce every value by 1, right? Similarly here, we go to the right side of here and reduce every value by 1. That's the simple idea. So you process the characters from left to right, you update the count array, you reduce their counts on the right side so that when you come to a character, you have already removed the left side characters. Let us now see implementation step by step. So after first loop, we have counts. After second loop, we have cumulative counts. So this tells me how many characters are smaller than or equal to n, and just index before tells me how many characters smaller than this. So just before, for n, this value will be 2. For m, it will be 2, right? For n, it becomes 3. So first thing we are doing is factorial 6. 6 characters are there, we compute factorial 6. Now we run a loop, right? We have cumulative counts, we have factorial, we have computed everything. Now we come here. We run the loop for I equal to 0. We update our multiplier variable, which stores the current factorial. We divide it by 6, we get 120. So we are processing the character s when we are here at I equal to 0. So we got the multiplier as 120. Now we get how many characters are smaller than this character s. For that, we just go to the previous index r, we get the count as 4. So we multiply this count with multiplier 120. So we get 4 into 120. So we get this value 480 plus 1, 481. So we get the value 481. Now we go to the next index t, and when we go to the next index t, we update the multiplier by dividing it by 5. So we get 24. And one more thing, when we process this, we reduced the counts of all the characters on all the indexes on right side of it. So we reduced this count by 1, so we got it 5, and we also reduced this by 1, so we got it 4, right? And we reduced it to 5. Everything basically, this is last index, so we are not going to use it, but everything was reduced by 1. So this was happened after you processed s. Now we have come to t. So when you come to t, you first update the multiplier, right? Now you add 481 previous result plus count of str t minus 1. So t minus 1 is 4, right? So you got the count of smaller characters on the right side because you reduced the count when you processed s. So we have 4 into 24 equal to 577. Now we update the counts of characters on right side of t. So you get the multiplier. Your multiplier is 2 now. Earlier it was 6. So you get the count as 595 plus 2 equal to 597. Now you move to the next character. And before you move to the next character, you update in values on the right of this character. So this character was I, right? At I equal to 3, we have I. So for I and on right side of it, we are going to reduce the values by 1. So it's going to become 1, it's going to become 2, it's going to become 2, it's going to become 2, 2, 2 and 2. Now we go to the next character n. When we go to the next character n, we count how many characters are smaller than this. So on the left of n, you must be having a value 1, right? So you get the value 1 and your multiplier must have been reduced by divided by 2 now. So it must becomes 1 now. So now your 597 plus 1 into 1, you get 598. And you run loop till n minus 1 only, because for this character, there won't be anything on the right side, right? So there won't be anything smaller. So we get the final result as 598, which is our lexicographic rank of the string. Now talking about the time complexity, this is constant work, assuming that character size is constant. So we create a constant size array, it's a constant work. This is big O of n work, right? We are processing through the string. This is again a constant work, and this is big O of n work. Although we have a loop inside it, but it's a constant loop, right? So n into constant is a n loop, right? So we have n work, constant work, n work. So we and overall our time complexity becomes big O of n. If we want to be more precise, if we want to include the characters also as part of the time complexity, then we can write the time complexity as big O of char to create this array and initialize it, then plus big O of n for this, plus big O of char again. So I'll ignore this. Okay, let me write it. Char plus n into char, right? n into char. We can ignore these because these are lower order characters, and we can say the time complexity is n into char. And if char is a constant, then we can say it's a linear time complexity. And auxiliary space requirement is big O of char. So we have talked about a linear time solution for the problem, which is a great tricky solution. Let us see this problem. We are given a string. We need to find out longest substring of the string which has all distinct characters. When we say substring, we mean consecutive characters. Subsequence means the characters may not be consecutive, but in case of substring, they have to be consecutive. Let's take this example. We have a string ABCD, ABC, and the substring, the longest substring, which has all distinct characters, is CDAB. So our answer is 4. Let us see this example. Here we have all same characters, so our output is 1. We have only one length longest substring which has all distinct characters. We can either pick this or this or this. In fact, in this example, we could take this substring also. This is of length 4 as well and has 4 distinct characters. Let us see this example. In this string, the maximum length substring that has all distinct characters is of length 4. This is also a possible answer. We can consider this string also as an answer with all distinct characters. Please note that if you take any other substring, either this substring will have duplicate characters or it will be of a smaller length than 4. For example, if you take AB, it has all distinct characters but length less than 4. If you take ABA, it has duplicate characters. So we need to find out longest substring with all distinct characters. Now please pause this video and try to write down a solution that takes a string as an argument and returns length of the longest substring with all distinct characters. We are going to talk about 3 solutions for this problem. One is big O of n cube, then the second solution big O of n square, then third solution big O of n. Let us first talk about a naive solution to solve this problem. Let's say we have this string ABAC. What we do is we consider all substrings of the string. First we consider all substrings that begin with A. The substrings beginning with A are A, AB, ABA and ABAC. For every substring, we check if it has distinct characters or not. For checking, we have written a separate function rDistinct that takes a starting index and an ending index, and it checks whether the string from index I to index j has all distinct characters or not. How does it check? It makes a visited array, Boolean visited array here. We have written this syntax in Java and this in C++. And whenever it visits a character from this index to this index, and if this character is already visited, it returns false immediately. Otherwise, it marks this character as true. So this is simple rDistinct function, and time complexity of this function is big O of n, where n is the total number of characters in the string. So this is a big O of n function that we have written here. Now what are we doing? We are generating all these substrings. And how are we generating the substrings? We fix the start index as I, we fix the end index as j, we consider the substring from I to j, we check if this substring has all distinct characters or not. If this substring has all distinct characters, we compare the current result with j minus I plus 1, where j is the ending index and I is the starting index. So our first substring is this one, and for this one I is 0 and j is 0, and our result will be initially 0. So when we enter here first, we update the result as 1. Then we come here, AB is the next string, I is 0 and j is 1. And we update the result as 2. When we come here, we notice that it does not have all characters distinct, so we do not go inside this if condition. When we come here, we again notice that it does not have all distinct characters, so we do not go inside this if condition. When we come to B, we go inside this if condition, but result is already 2 here, so we do not update the result. For BA, again result is already 2, so we do not update. For BAC, we go inside this if condition because rDistinct is going to be true here, and we are going to update the result from 2 to 3. Now we are going to come to A, for which we are not going to update the result. For AC also we are not going to update. For C also we are not going to update. So by the end of this function, we'll have our result as 3 for this string BAC. Let us now talk about time complexity of the solution. In this solution, we have two loops, I equal to 0 to n minus 1, j equal to I to n minus 1. Inside these two loops, we call a function R distinct, which has time complexity as big O of n. So our overall time complexity is big O of n cube. Now please pause this video and think of an approach which is better than big O of n cube. We are going to talk about two more solutions. One is big O of n square and one is big O of n. Let us now talk about a better solution. Time complexity of the solution is big O of n square. In this solution also, we consider all substrings. We run two loops, 0 to n minus 1 and I to n minus 1. We consider the substring from I to j and check if it has all the characters distinct or not. In the naive solution, we were calling a function R distinct which was traversing through every character from I to j to check if all these characters are distinct or not. Here what we are doing is, for every value of I, we are using one visited array rather than using one visited array for every substring. Because when you fix an I, what you do is you keep on adding characters, right? So your I says initially 0. So you are initially, j is also 0. So this character is your initial character, or this is your initial substring. Then you extend and add b. So you need to add b also to your visited array. Then you add a. When you try to add a, you see that this is a repeating character. You simply break the loop, right? You do not proceed further. So you basically are not going to consider a, b, a, c. That is what we did in the naive solution as well. When we come to b, we create a new visited array. So when we are adding a character for the current starting point or the current I, we simply mark it as true. And if it is already marked as true, we break the loop. And when it is not marked as true, it means it's a different character and all the previous characters must also have been different, right? Otherwise we would have broken the loop. In those cases, what we do is we compare the current result with the length of current substring, and if the length of current substring is greater, we update the result. And at the end, we finally return the result. So this is a better solution. Now please pause this video and think of a solution that is big O of n, even better than this. Let us now talk about an efficient solution to solve this problem. The idea is to compute this value max and j for every index j, where max and j is length of the longest substring that has all distinct characters, and this substring ends at index j. Let's see with this example. We have the string ABC, A, B, B, D. Longest substring that ends with A and has all distinct characters is 1. For first character, it's always going to be 1. Longest substring that ends with B and has all distinct characters is AB. For C, it's ABC. For A, this is BCA. For D, this is BCAD. The string must end with this index and should have all the distinct characters. For B, the string is CADB. For D, the string is BD. So if I compute all these values for every index, I simply need to return maximum of all these values at the end. So our result is maximum of max and j, where j goes from 0 to n minus 1. So we are saying that this solution is going to be big O of n, and we are going to compute max end for every index from left to right. So this max end for the current index should be computable in the constant time. How do we compute this in constant time? The idea is to use the previous value of it. So if you are at index j, you can use max end j minus 1 to compute max end j. Max end j minus 1 is the length of the longest substring that ends with index j minus 1 and begins at some index I. How do I use this length to find out max end j? See, if this character xj does not appear in this string at all, in this string from xi to xj minus 1, then my result will be max end j minus 1 plus 1. If strj is not present in the string max end j minus 1, right, in this string from I to j minus 1. If it is present in this string, then it will be from that index to xj. And what will be that index? That index will be previous index of the character xj. The index at which this character xj appeared just before this occurrence at index j. So if I somehow get this index in constant time, I can do j minus previous of strj plus 1 to get the length of the longest substring that ends with j if this strj or xj appears somewhere from I to j minus 1, where I to j minus 1 is the longest substring that ends with index j minus 1. Now the question arises, how can we figure out if this character strj was present in this string from I to j minus 1 or not? For this purpose, we can again use our previous of strj. If previous of strj was less than I, then this was not present in the previous this string, otherwise it was present. So we use this previous of strj for two purposes, and previous of strj for every character can be computed and can be obtained in big O of one time. We just need to use the character as an index in a previous array, and whenever we find the character, we update its index in the previous array as a previous index. Now please pause this video and try to write down complete code that takes a string, returns the length of the longest substring with all distinct characters in big O of n time. Let us now see implementation of the efficient approach. We traverse the input string from j equal to 0 to n minus 1. Every character at index j is considered as the last character of the substring. We find out length of the longest substring that ends with j and has all distinct characters. We call it maxend. So we are going to compute maxend for every index j, and we are going to compare it with the result. If result is smaller than maxend, then we are going to make the result as maxend. We simply take the maximum of result and maxend. Let's see this example. Max end for this index is 1. Max end for this index is 2 because there are two distinct characters. Max end for this is 3. Max end for this is also 3 because there are three distinct characters in the longest substring that ends with this A. Max end for D is 4. Max end for B is again 4. Max end for this last D is 2 because there are two characters that end with D and have all distinct characters. So we compute maxend and we take the maximum of all the maxends. To compute the maxend, we need starting index and we need the ending index. We already have ending index as j. Now the question arises, how do we compute the starting index? To compute the starting index of current window, we use two values. One value is previous starting index that we did for the previous window for index j minus 1. Right? We run from j equal to 0 to n minus 1. So when we are at current j, we must be having starting index for j minus 1. The other value that we use here is previous index of strj. strj is the character that we are currently adding to this window. We find out when did this appear last. If it appeared before the starting index or at the starting index of the previous window, then we need to extend the previous window. Otherwise, we need to keep the previous window as it is. Let's understand this with this example. We have the string ABC, ADB, D. We initialize previous of every character as minus 1. We initialize starting index as 0, initialize result as 0. We begin with this character. For this character, starting and ending, both indexes are 0. So we compute our maxend as j minus I plus 1, which is 1. Now we compare it with the result. Result is 0, so we get a greater value. So we update the result as 1. We mark the previous of A as 0. Now we go to the next character, j is 1 now, and we compute this value, previous of this character, and we compare it with the previous starting index. So previous for every character is minus 1, so it's minus 1 for this also. So starting index that we are getting is minus 1 plus 0, so we get the value as 0. And starting index, current starting index is also 0, so we get the starting index as 0. Now we do j minus I plus 1, we get the max end as 2. So we get the length as 2 for this index, right? And we compare it with the result. It's greater than the result, so we update the result and we update the previous of B. Now we come to C. When we come to C, we again do the same thing. we compare, we find out the previous index of C. C was not there at all. So previous of C will be -1. -1 plus 1 will be 0. If we take the maximum of 0 and 0, we'll get 0. So we are going to get the starting index again as 0. So length of the longest substring that ends with C is 2 minus 0 plus 1. So we get the length as 3. And this is greater than result. So we update the result. And we update previous of C also. Now we come to A. And this is where we get an interesting case. Starting index of the previous window is 0. But previous of A is also 0. So we get 0 plus 1 here. So this window for this character has to start from 0 plus 1. We are taking the maximum of two values. So we get the starting index as 1. We have J as 3. We get the length as 3. Right? So for J equal to 3 for this character, we have the max ending as 3. It's not greater than result. So result is going to be 3 only. We update the previous of A. Now we come to D. D did not appear at all. Previous of D will be -1. So you will not be changing the starting index of previous window. You will be keeping it as it is, B only. And you will find the max end as 4. 4 minus 1 plus 1. You will update the result and you will mark the previous of D as 4. Now we come to B, and this is again an interesting case. B has appeared before. So your starting index will change to C. Now, right? How did this change to C? We got the previous of B as 1. We add 1 to it, we get 2. Which is greater than the starting index of previous window. Starting index of previous window was 1 and now we are getting 2. So this is our new starting index for this. So what is the length we get? We get the max end as 4 now, which is not greater than the result. So we do not update the result. We update the previous of B as 5. Now we come to this index, and for this index, we compute the previous of D. Previous of D is 0, 1, 2, 3, 4, 5. We have already computed it here. Now we come to the last index and we compute the previous of this character D, and we get the previous of D as 4. So we use previous of D plus 1, which is 5. So we get the starting index as 5. Please note that we are taking this value because starting index of the previous window, the previous I was this index, right? And this index is definitely greater. So we are taking it 5. And the max end that we are going to get is this one, 2. 6 minus 5 plus 1. And this is definitely not greater than result. So we are going to keep the result as 4. And we are going to update the previous of D as 6. So this is how this algorithm works. It gives you the result 4 for the string, which is your final answer. You have multiple strings of distinct characters with length 4. These are the multiple answers we can get here. Let us now analyze time complexity of the solution. We are simply running a loop, and inside this loop we are simply doing indexing in the string, which is big O of 1 operation. So overall time complexity of the solution is big O of n. We have talked about 3 solutions for this problem. One is big O of n cube, then big O of n square, then big O of n solution.